that made this work possible. And I just wanted to highlight Dr. Mayra Gonzalez Martin, Cesar Victoria Ceballos, and Yaherlin Diaz, who are also participating in this conference. So just to give a little bit of context, one of the complementary models to the unification scheme is the outflow model proposed by Elvis in 2000. And in this scenario, both the broadline region and the torus are formed from a wind that is coming off the accretion disk. So as long as this wind keeps coming off, the radiation pressure will be able to counteract the gravity, and otherwise these regions would eventually collapse. And in fact, some theoretical predictions by Elitsur and collaborators in 2006 proposed that these regions should not exist for volumetric luminosities below 10 to the 42 ergs per second. However, observational results suggested that high accreting sources in some cases might actually miss these regions. This is the case of the true type 2 AGN, in which the broadline region is intrinsically missing. In fact, in 2016, Elitsur and collaborators, again through theoretical predictions, proposed that this is indeed a much more complex scenario, and that the disappearance of the torus actually relies on the wind parameters, including the efficiency, the density, the radial extent, that it could ultimately be parameterized with this lambda factor, and that in fact in the luminosity mass diagram, there is like 3 regions. The first one is demarcated by this red line here, and below this line, all the sources would miss the torus. And on the other hand, above this red line over here, the sources always present the torus. One interesting region is the region between these 2 lines, the one that I am showing here. And in this region, the existence of the torus and the broadline region depends on these wind parameters. And in fact, these black dots that I am showing here are through type 2 AGN, which, as you can see, fall in this region, and therefore it reinforces the idea that the scenario is much more complex than just depending on the accretion rate. One of the main ways to study the torus is the mid-infrared wavelengths, because it's mainly composed by dust and it peaks at these wavelengths. And one very nice result is the one that I am showing here by Gonzalez Martin and collaborators in 2017, in which they selected a sample of Lehmer and Seifert objects in order to trace a possible disappearance of the torus. And one very interesting result is that most of the sources fall exactly in the region in which this depends on the wind parameters. They also find 13 candidates for the torus disappearance, and these are the sources marked with these black dots here. As you can see, most of the sources fall below the region, and this is in agreement with the theoretical predictions. Let's remember, in this region, the torus must not exist. However, they find 5 sources that fall in the region in which the torus may or not exist, and this is in agreement with the idea that this depends on the wind. So with this in mind, our main goal is to trace a possible disappearance of the torus at X-rays, which is possible through the reflection component. And we do this with NuSTAR because it provides the spectral range necessary that goes from 3 to approximately 79 kiloelectron volts, which is necessary to detect and characterize the reflection feature. So I know that all of us are very familiar because we have been seeing these images a lot in this conference, and I just wanted to point out that what we are looking for is, of course, the intrinsic continuum that is modeled with a power law, and the reflection component characterized by 2 main features. The first one is the iron K alpha line at 6 kiloelectron volts, and the second one is the reflection hump that peaks between 10 and 30 kiloelectron volts, particularly important for very obscured AGN. So our sample was taken from the NuSTAR database. We selected sources with below 200 megaparsecs. This was intended to do because we want to study the local universe. Moreover, we only selected sources with black hole mass measurements because we want to check if there is a evolutionary trend. And we only kept sources with Eddington rates below 10 to the -3. However, I want you to know that we calculated this Eddington rate a priori through the observed X-ray luminosity. And this has an impact because once we take into account the obscuration, the Eddington rates will increase depending on the obscuration in the line of sight. So as you can see, we have a wide range of black hole mass and volumetric luminosities. In particular, for the luminosities, we see a trend towards lower luminosities, and this is because we actually impose a criterion on this parameter. Our sample consists of 81 sources. So the next thing that we did was to fit our spectra to a set of models. The first one is a model accounting for the intrinsic continuum that is obscured with a partial covering scenario, represented with the obscuration in the line of sight and a power law, and also a constant that is multiplied by the same power law, and this constant is actually accounting for the partial covering. We also added two Gaussian line profiles, which are commonly in the AGN, are commonly present in the AGN. Now, our second model is the first one in the addition of a reflection component, in this case is XRAF, which is reflection from cold neutral material. And as you can see, we also add a Gaussian profile centered at 6 kilo electron volts, which refers to the iron K alpha line. And we also use a third model version, which is again the M1, and an addition of a reflection component, in this case is PEXMON, which is just a modification of PEXRAF that accounts for the iron K alpha line. And it actually fixes the contribution in the iron K alpha line with respect to the Compton shoulder. Now, in principle, both of these models can be treated equivalently. And in fact, we base our analysis in the M3 model version, but we use the M2 model version because we want to make a proper analysis of the iron K alpha line and to see how it contributes in the reflection spectrum. Now, what I am showing here is the M1 model version and M3 model version applying to NGC 7582. As you can see, there are some residuals when we only use an absorbed power law, mostly around 6.4 kilo electron volts, which are somehow improved once we take into account the reflection component. One thing to notice is that we do not use more sophisticated models as the ones that have been presented so far in this conference, mostly because the signal to noise rate of our data is rather low, and we do not want to maybe underestimate or not properly estimate the spectral parameters. And also because our aim is to see how much the reflection contributes and how we can trace a disappearance of the torus rather than to geometrically characterize the torus. However, I invite you to stay for Jaher's talks today, which is right after me, and where they actually use geometrically motivated fits for low luminosity AGN. Now, we base our analysis on the existence of the reflection component on three criteria. The first one is that M3 is statistically significant over M1, and to do this, we use the F-test. The second one is that the 6.4 kilo electron volt line is restricted in normalization so that we can calculate the equivalent with the luminosity of the line. And the third one is that PEXMON is also restricted in normalization so that we can calculate the luminosity of the component. Now, our first result is that we find 11 candidates for the torus disappearance. And this is the spectra that I am showing here. So these are the objects that are candidates for the torus disappearance. As you can see, most of them can be fitted with a simple power law. In fact, most of them do not present obscuration in the line of sight, or the obscuration is very low, sorry. One object that comes to our eyes is NGC 612, which actually seems to have a high obscuration in the line of sight. In fact, we search in the literature and previous results suggest that the obscuration comes from the host galaxy rather than from the AGN itself. So it still fits with the idea that it's not coming from the torus. And the second one is NGC 7331, which with a prominent ionization line. However, this line is in fact the 6.7 kilo electron volt and not the 6.4. So all these objects do not present any trace for the reflection.
5 minutes.
Thank you. Now, we do not find any direct correlation between the reflection and the accretion mode. This is a very important result. Moreover, we find that when the reflection exists, it contributes for around 40% of the intrinsic continuum. And we also find that the contribution of the iron K alpha line seems to be changing in a range between 1 and 10%. So this is our most important result. What I am showing here is the luminosity black hole mass diagram. And just for comparison, we also plotted the sources in the vast sample. As you can see, these sources tend to have, in general terms, higher accretion rates, which are demarcated by these black lines over here. And then again, the region between the two red lines is the region in which the torus may or not exist. We also plot the sources from Gonzalez, Martin, and collaborators in order to compare the mid-infrared results with our own. The green squares are the resources, are the sources with a reflection component, and the red triangles are the candidates for the torus disappearance. So the most interesting result here is that all our samples fall in the region in which the torus may or not exist, even the candidates for the torus disappearance. This is still in agreement with the theoretical predictions. We do not see any evolutionary trend. As you can see, both low accreting sources and kind of high accreting sources in some cases present or are lacking the torus. And also very interesting is that we do not have any sources in common with the results from the infrared. And this makes us think what will happen when we have observation at X-rays for some of these sources and how they will behave in this same diagram when analyzed at X-rays. So the other result is that when it exists, the reflection accounts for around 40% of the intrinsic continuum, and this is seen with this red dotted line over here. And more interestingly is that we find a change in the contribution of the iron K alpha line compared to the overall reflection component. So as you can see, it ranges between 1% and 10% of the reflection component. And in fact, it seems to have a little impact on the reflection component for larger reflection luminosities, which is translated into higher continuum luminosities. And it seems to have a larger impact with lower reflection luminosities, which translates to lower intrinsic luminosities. So this makes us think that there may be a transition on the chemical composition of the torus towards lower luminosities, which actually should or can be checked using other wavelengths as well. So thank you. Just to finish, 80% of the sample is obscured at X-rays. This is in agreement with previous results. The peak of obscured sources occurs at Eddington rates of around 10 to the -3. And we also find that 20% of the sample are Compton-thick sources. This is a very nice result because it actually is in agreement with much more complete sample. For instance, the vast sample, in particular, the results by Ritchie and collaborators in 2017. Which are these red and blue areas at the back. And as you can see, our sources, Compton-thin sources, which are represented with this dashed line, seem to peak at around 10 to the -3, while the Compton-thick sources, which are represented in this dotted line, the percentage at around 10 to the -3 is of around 23%, which is kind of in agreement with what has been found in previous analysis, for instance, this one. So I will leave my conclusions. We find that 50% of our sources lack of reflection signatures, which suggests the disappearance of the torus in these sources. Our sample of candidates lies in the region in which the torus may or not exist, according to the theoretical predictions, but we do not find any evolutionary trend. When it exceeds, the reflection accounts for 40% of the intrinsic continuum. Our results suggest a possible chemical transition of the torus toward lower luminosities, and 80% of the sources is obscured at X-rays, in agreement with larger samples. Thank you very much.
Okay, do we have questions? Go ahead, Peter.
Hey, Natalia, it's Peter. Very nice. I was curious. Do you see any relations with the iron K alpha equivalent width and luminosity?
Thank you. Yes, we actually checked this relation. Sorry, this is a hidden figure. So we also checked the relation that is found and that has been predicted. there is a general trend of correlation, of course, because we are using such a simple geometry. We are not able to reproduce the theoretical predictions that, for instance, are described with these blue and pink lines over here. But we see that at a certain reflection where we have, I don't know how to say it, we have some sort of, okay, no, for certain obscuration, we do not see any more changes in the equivalent width. But yes, we attribute this behavior to the fact that we are not using more realistic geometries for the torus.
Cool, thank you. Cheers.
Thank you.
Okay, any further questions? Let's see, I don't see anything online. Let me just check the chat here. Okay, no further questions?
Thank you.
All right, let's thank the speaker again. Okay, so our next talk is Diaz X-ray reflection and low accretion rate AGN with XMM-Newton, NuSTAR, and Swift. And I will likewise try to signal you in 5 minutes left.
Okay. Good afternoon, everyone. My name is Yaher Lindia. Everyone can call me Yaher, it's fine. So today I'm going to present my recent work studying the reflection in a sample of low luminosity agents using a sample from XMM-Newton, NuSTAR, and Swift. Well, let's see. Well, Claudio already made a big introduction about this in the morning, so I will pass a little quickly about this. But he found that apparently there is a relation between the fraction of obscure sources and the accretion rate, where galaxies in this region are high luminosity agents, where apparently this torus or this structure will be pushed by the effect of outflows. On the other hand, galaxies in this region are low luminosity agents, which apparently have a different configuration compared with high luminosity sources. Apparently, galaxies in this region can be content covering a large fraction of the sky, or there are so many works pointing out to an apparently disappearance of the torus. So we will check that. So a tool to infer or study properties of this structure is, of course, the X-ray spectra. In fact, in the AGNs, we have many features that we can find, but here I will show you the main ones. For example, here in green, you have the emission that is coming from the corona, which is a structure located more or less above the central engine. So apparently the UV photons coming from the AGN will be interacting with this corona, producing the power law emission that we observe. And in fact, this is described by the slope of this emission called the photon index or the spectral index, and the rollover at higher energies called the high energy cutoff. Also, these photons will be interacting with the circumnuclear gas, like the accretion disk, as can be seen here in pink, or in fact, more distant or neutral material like the torus. So as can be seen here, it shows different features depending on the ionization degree of the material that is reflecting the material. And this is called, in fact, the reflection. And Natalia already talked a lot about this, but only you have to keep in mind that this is described basically by the quantum hump observed to a higher energies and the iron alpha emission line peaking around 6.4. So in this work, my aim is try to put some constraints on properties of these types of reflectors. So to do this, I'm mixing or combining observations from XMM-Newton and NuSTAR. And it's pretty clear why it's so important to combine these kind of observations to explore properties of the torus in this beautiful plot. This is a simulation for a different configurations of the torus. In blue, you have the emission coming from the central engine, and above, you have an torus which have the same column density, but cover different range of the sky. Torus here is covering 25%, and here is covering only 5%. On the other hand, in this panel, we have an torus which covers the same range of the sky, only 50%. It has different column density. This is an torus content thin, and this is an torus content thick. Content thick, this is a column density 10 to 24. So if you see the energy range below 10 keV, for example, in this plot and in this one, I mean, you don't see the quantum hump, so you cannot separate between both scenarios if you don't see that energy tail, high energy tail in your spectrum. Also, if you see only energies above 10 keV, you will see only the quantum hump, and you will basically blind for the iron alpha emission line, and you don't see that. So you cannot separate, for example, in this one or in this one, or between this scenario. So this shows the importance to combine this kind of data. And also, there is an important thing that we can also estimate with this model, that is an emission coming from the central engine, as I said before, described by the spectral index. This trend was previously found for analogy with the X-ray binaries. This break that is observed close to -3 points out to an apparently change in the accretion physics between high and low luminosity sources. Galaxies in this region are high luminosity AGNs accreting very efficiently with the classical accretion disk. On the other hand, galaxies in this region are low luminosity sources which are not accreting very efficiently, probably dominated by an EDOF. However, if you look at this plot, you can see that it shows a very high dispersion in the low luminosity branch, which can be associated, in fact, with some intrinsic property of the galaxies or the sample, or in fact could be related with the sensitivity of the data, because the previous work only used XMM-Newton observations. So my goal also is try to understand this dispersion. And to do that, I use a sample from the BAS data release 2. I select all the low luminosity AGNs with accretion rate below 10 to minus 3, sorry. This sample is like 23 galaxies, and I check in the archive which galaxies of this sample has NuSTAR plus XMM observations. In the end, I have a sample of 17 galaxies. One of these galaxies we have property data. These are some general properties of the sample. For example, the supermassive black hole, which was obtained from the BAS data release 2, obtained from the literature. And these are the accretion rate, which of course is below 10 to minus 3. And it was estimated using the volumetric correction close to 20. And using the luminosity between 2 and 10 keV from the Swift BAT observations. So great, we have our data, we process our data, we have everything. Which is the next step? Define a methodology. So we have XMM and NuSTAR data. This data could be simultaneous, or in fact not. It could be separated by years, by months. So the first step in our work is try to understand what happened with this not simultaneous data. So we take this observation, which were 6 galaxies in our sample, and study the spectral variability. Basically, we take the XMM and NuSTAR data and restrict the energy range in the range when they overlap, and fit an absorbed power load to see what happened. We start setting as a pre-parameter the column density, the photon index, and the normalization to see which one is the best configuration to describe the data. In the end, only 2 galaxies in our sample are varying between the spectra, showing only variations in flux. So that was considered in our spectral analysis. The second step was the spectral analysis. Of course, the first thing that you have to keep in mind is the emission from the AGN, which we modeled with an cutoff power law, in fact, an absorbed cutoff power law. And I can show you here, this is the purple emission. And also the reflection, which is this orange emission. We use 3 different reflection models. PEXMON we use only for comparison with previous work in the literature because this is a most simplest model. But as we are interested in the geometry and the properties of the reflector, we need more sophisticated and more physical models. So to do that, we use Borus. Ms. Lab talked a lot about this model yesterday, but basically it is, this model describes a smooth distribution of a torus with a polar cutoff. Between the parameters that this model has is the inclination, the covering factor, and the column density. And also, to model the accretion disk, we use Silver, that is a model from Javier. And here I put just an example to see how are the spectra depending of the ionization degree of the accretion disk, where if you have a highly ionized accretion disk, is mostly acting like a mirror. Javier talked a lot about this, so I won't explore so much about this. So the other thing that we tried to do, we did in fact to model our spectra, was study the soft excess in order to put good constraint on spectral properties. This is the emission of I show here in red. So we use 3 different models, and a scatter power law, and a thermal emission modeled with a metal on and a warm ionized absorber. So, okay, we have all our spectra fitted with all these models. So the first thing that we observed is when we fitted the accretion disk, we found that the parameters were highly unconstrained. Unfortunately, we couldn't constrain anything about the accretion disk. But for the torus, yes. Unfortunately, for the covering factor, we didn't find anything because it was highly unconstrained. But for the column density, we found something. This is the correlation between the column density of the torus light reflector and the accretion rate. And well, my points are the pink one, and the yellow are the point from Esparza et al. And in blue, there are the VNet data points, and in black is my correlation. Even with this big dispersion that we found, and with this small sample, we found that probably there is some relation between these parameters. And keep in mind that in this case, we have a covering factor as a free parameter. So this is valid for any coverage of the torus. Thank you. So apparently, what we have is when we see a torus in this low luminosity regime and apparently disappears, it's not disappear at all. In fact, this is a lower column density. This is what happened in that regime. But we need more data, of course, to improve our relation. And also, our work allows us to study the spectral index. So this is our correlation. In blue are my data points, and in yellow, the Esparza et al. Data points. And these are a lot of correlation which were previously found in the literature. So the first thing that we have to keep in mind is, well, we confirm in fact, that there is a break in the correlation between spectral index and accretion rate in 10 to -3, probably related with some kind of change in the accretion physics between high and low luminosity sources. And also, looking the plot of Che et al. In 2018 and my plot, you can see that apparently there is an improvement in the scatter, which was previously found. So the question is, why? Why? Is this a result of the inclusion or a combination of XMM and NuSTAR data? Or this is in fact a result of the very sophisticated reflection models that we use? So to explore this, I plot here the data point from the BAS data release 1. In this work is from Claudio 2015, using PEXRAP and without NuSTAR data. And in red is our work using PEXMON and with NuSTAR data. And what we found, if you compare this plot and this one, you can see that in fact there is an improvement in the scatter. Even with the, I know there are not so much points, I know, but there is an improvement in the scatter and in the error bars. So including or combining XMM and NuSTAR data leads to a better estimation of the spectral index. And also, I compared what happened with a more sophisticated model like torus. Well, we found that, of course, improved even more the error bars and the scatter. So just to finish, well, our sample has 17 galaxies. In all this sample, 12 are equally well fitted with a disk or an torus. We cannot separate between both scenarios because from the statistical point of view, they are the same. So, however, for the disk, we could not constrain anything, but for the torus, we have some constraints in the parameters. So for that reason, I focus most in the torus. For 5 objects, we clearly separate between the disk and the torus, and in fact, we found that the torus is the best representation of the data. And considering a torus to the best representation of all the sample, we found that apparently there is a relation between the column density and the accretion rate, where apparently the low luminosity sources tend to have a lower column density compared to high luminosity sources. So the torus apparently doesn't disappear. It only changed its properties. And also we corroborate the previous correlation or the break in the correlation between the spectral index and the accretion rate that points out to a change in the accretion mechanisms in these galaxies. So I have to say thank you, and thank you, organizers, and thanks for all the NuSTAR team for the effort and all the work.
Thank you. Okay, we have time for questions. Anybody come up to the Javier? Looks like you.
Very nice talk, Jaher. I was wondering, I don't know if you mentioned it and I missed it, but if you see a correlation between NH and gamma and the photon index, because I would expect a bit of a bias in the model. If absorption is very high, then you might end up having a different constraint on the slope, and that might affect the correlation, the real correlation that you're trying to find.
Did you mean a correlation between the NH or
the column density?
In the column density in the line of sight,
Right.
and the photon index?
And the photon index.
No, but I found a correlation between the column density in the line of sight and the reflector. I didn't put here because I don't have time, but I can show you.
All right, thanks.
I can show you if you want. That's very interesting. Very quickly.
Okay, let me just check the chat online. Okay, it looks like we have a hand raised. Jen Chen,
Yes,
do you want to
Yeah.
speak?
Yeah.
Okay.
Can I ask a question? Have you ever thought about comparing your gamma versus Eddington ratio plot with X-ray binaries? Because X-ray binaries, for example, and my impression is that during the quiescent state, the power law continue, which is the Eddington ratio is very, very low. The power law is actually softer than the gamma, around like 1.5, around that in the hard state, which is around 1% of Eddington. So is it like similar to what you are seeing here in the sample of AGN?
Well, I didn't compare with X-ray binaries. I only say because this believed that apparently this break that we found in AGNs is the same that we found in X-ray binaries, because we believe that AGNs are scale versions of X-ray binaries by mass or luminosity. However, I compare my data with some previous work, but also with AGNs. I found that they are mostly consistent between them. I don't know, but with X-ray binaries, I didn't compare.
Okay, yeah. I'm just saying that because in the quiescent state, it's not necessarily all the lamppost corona, all of these things is doing probably the ADAF model or something, probably more important in the quiescent state. So like below the brick, like below -3 over there. So you're probably looking at something different. That you already hinted on that. You're seeing that different accretion physics. So yeah, I just want to comment on that. That's it. Thank you.
Thank you.
Okay, one last question, Thomas. Do you want to?
So on what you have up here right now, comparing to the schedule, do your data provide a statistically significant differentiation between just a single fit to gamma Eddington ratio?
Unfortunately, our sample is very small, so it's not statistically significant. So our plan is try to expand our work to a more complete sample in order to better constrain everything, but it's just the first step.
Okay.
But apparently there is an improvement. It's like a pilot project.
Yeah. Okay.
Okay, let's thank the speaker again. Great, and now for something completely different. We are going to hear about NuSTAR's observations of Jupiter's aurora from Kaya Mori. Let's see, we've got you. Can you say something so we'll make sure we got sound?
Hi, everyone. Can you hear me?
Yeah, great. Okay.
And can you see my screen?
Yes, we can see the screen.
Okay, great. So let me start. So hi, everyone. I believe this is going to be the final science talk. I bet everyone's tired. And if you need a break from hearing about AGNs, X-ray binaries, or relativistic timelines, this is a talk. I'm going to be talking about something very different. It's about Jupiter. And then I'm going to highlight NuSTAR's unique and important role for understanding of planetary science, especially for the Jupiter in the next 20 minutes. So we published a paper in Nature Astronomy and also had a press release back in February. On the lower right, you can see a cartoon from the press release. So NuSTAR detected hard X-rays from Jupiter. So I'm going to talk about this. So let me start with some basic facts about the planet. Jupiter is a giant gaseous planet, mostly made of hydrogen and helium. Let me show you a beautiful video from Juno flyby, very close to the planet right now. So you can just enjoy the video for 1 minute while I'm talking about the planet. So Jupiter rotates at about 10 hours spin period, and it has a magnetic field of about 4 Gauss, which is about 10 times higher than geomagnetic field. Jupiter has 79 moons, including 4 inner moons discovered by Galileo. So over the last 5 or 6 years, Juno mission from NASA has been orbiting around the planet continuously every 50 days or something. They reach the Jupiter at the closest contact at about 2 or 3 Jovian radius. So these are the pictures you're seeing from the Juno's perijobs. Again, that's the closest point to Jupiter. So Juno carries 9 instruments, including radio, UV, infrared instruments, and then gravity measurement device and magnetometers, but it's lacking any X-ray detector. So that's why it's really important to have a coordinated observation campaign with Juno, including NuSTAR. So you maybe heard about Jupiter's aurora emission. So unlike the Earth's aurora emission, which you may or may not see it, depending on the solar winds coming through the polar regions, Jupiter actually emits a persistent aurora emission from both north and southern poles. So you can see a beautiful UV image, a movie from HST on the right. So this is just showing the northern aurora, but you can see in the zoomed image on the left, so aurora has some structures here. So you can see a main UV over here, which is very persistent, the strongest emission across the different wavelengths. And then different parts of the aurora are actually connected to the inner moons like Io, Ganymede. So you can see their footprints. So again, I show you the movie here. So the UV over here is very persistent. It doesn't really change over time. But in the polar region, you start seeing some time variability because solar wind particles coming in through the open field lines, and that's usually variable over time. So you start seeing some different components here. Okay. So what about X-ray? So we have about 40 years of history about X-ray observation. So the very first discovery was done by Einstein telescope back in 1983. And then Rosat also detected soft X-rays from the planet. And then Chandra and XMM detected X-ray emission from different places on the planet. So as you can see on the right, that's the Chandra image from Gladstone et al. 2002 paper. So in the main body, that's for the disk emission, that's basically reflecting or scattering solar X-rays. In the North Pole and the South Pole region, you have aurora emission much brighter than the disk. And then that indicates that Jupiter can self-generate X-rays from the aurora. So before I talk about how X-rays are generated from Jupiter, let me talk about this very peculiar moon called Io. Io is the innermost moon. Then it orbits actually inside the magnetosphere of the Jupiter. And then it's so close to the planet it feels enormous tidal force from Jupiter. So that makes this planet volcanically very active. So there are hundreds of volcanoes here. As you can see in this picture, you can see one eruption coming out of one of the volcanoes here. So that means Io is injecting almost continuously tons of silicon and oxygen into the magnetosphere at the rate of 1 metric ton per second. So that's a lot. So that means Io produces a big plasma torus, as you can see in this cartoon, that's in red. So it's spreading out by centrifugal force. It's still in the magnetosphere sphere of the Jupiter. And then these particles actually get accelerated along the magnetic field line and eventually precipitating into the Jovian atmosphere, and then produces all these UV and the X-ray emission from the pores. So let me just give you some historical view of Jupiter Io system. So back in 1969, Goldreich and Lindenberg modeled this Jupiter Io binary system as a unipolar inductor. So basically the idea is you have two conductor like planets, and moon connected by a magnetic field, and it's rotating from each other. And then you start having a DC current around the system. So that means you can accelerate particles coherently, somewhat like a DC current. And then I just want to note that this particle flow is not caused by accretion due to gravity. It's more like electric particle flow. So that's a very classic view of a Jupiter Io system. But in more recent years, people just realized that this is more complicated, more dynamic. So there are more advanced MHD theories, talking about stochastic particle accelerations from MHD waves, magnetic reconnections, all kinds of plasma modes. So, and they're also supported by observations, especially from Juno. So the story is more complicated than that, what Goldreich and Lindenberg predicted back in 1969. So how do you actually produce X-rays from the aurora region? So there are some predictions back in 1990s. So there are 3 papers talking about this. So basically what happens, you have electrons and energetic electrons coming into the atmosphere after being accelerated in the magnetosphere. And they assume the Maxwellian electron energy distribution, which follows this equation. That's understandable because at that time, people assumed electrons are accelerated by this DC current, coherent acceleration. And then these electrons are going to the atmosphere and then emits the brimstone X-ray emission after hitting hydrogen and helium. So these papers are making a prediction for the Ulysses mission, which was visiting Jupiter back then. But unfortunately, Ulysses didn't detect anything. But they put some upper limit, which we're going to be using later on. So that was a disappointment in theoretical side. And then as far as I know, there was almost no theoretical model for X-ray emission from Jovian aurora over the last 3 decades. So now I'm going to be talking about early 2000 when XMM and Chandra started looking at the planet. So XMM had this more like 0.2 to 7 keV spectrum from southern aurora, which you can see on the right. So what they found out is there's a dividing line at 2 keV. Below 2 keV, the X-ray is dominated by charge exchange lines due to silicon, sulfur, and oxygen. And above 2 keV, where you don't see any of these lines from these ions, there seems to be some continuum emission up to like a 7 keV. You can see 7 or 6 beams above 2 keV. So, but with these limited number of beams, you cannot really tell if the continuum emission is thermal or non-thermal or how high energy does it extend. So we clearly need NuSTAR observation, and that's what we did. So there was a big campaign of NuSTAR observation of Jupiter from 2015 to 2018. Back in 2015, that was more like a pilot program. We wanted to see Jupiter just for 100 kiloseconds, see what's out there. And then interestingly, we found hard X-ray emission from the southern pole with 3 sigma. And then we proposed for more observations for AO3. So fortunately, it was accepted. So we had a total exposure time of 600 kiloseconds. And then each observation is actually very difficult because you need to track Jupiter as Jupiter is moving. So thanks to NuSTAR SOC and Brian Griffenstadt, we were able to nicely schedule the observations. And it's one of the observations you can see on the lower left. So you have multiple tiles capturing Jupiter. And then Jupiter, you cannot see the Jupiter because Jupiter is moving in this plane. So you need to correct for this motion by going to the Jupiter's moving frame. So it takes some effort to do this, data analysis.
5
So
minutes.
Let me show you, let me show you some results. So NuSTAR detected hard X-rays from north and southern pole up to 20 kb. So that's a beautiful NuSTAR image in 8 to 20 kb band. So you can clearly see separation between the north and south emission. And then by combining all the observations, we got about 727 net counts. And then it's interesting to see that the southern aurora is brighter by 30% compared to northern aurora. This is actually contrary to the below 2 kb band image, because below 2 kb, the X-ray emission is dominated by the ion emission, and above 2 kb, it's dominated by electron bremsstraum. And then what's interesting is we got the broadband X-ray spectrum from a simultaneous XMM and NuSTAR data. So it fits to a very hard power model with photon index of 0.6. So now we have to deal with very flat X-ray spectrum trying to explain this. So now we have a modern version trying to model this Jovian aurora X-ray emission. So we have 3 steps here. So we have direct and simultaneous electron measurements by Juno. That's number 1. And number 2, we use the Giant for Monte Carlo simulation to model the particle transportation of the electrons going into the atmosphere and emitting X-rays. So that's best done by GN4. And then we produced a bunch of simulated X-ray spectra and compare them and fit them to the data. So this work was done by our student, Gabriel Bridges. So let me show you some results here. So yes, so first step is trying to analyze the electron spectra taken by Juno. So Juno carries 2 particle detectors. One is Jade. Its energy band starts from 0.100 kb, and Jedi is another instrument which covers a higher energy up to 1 MeV. So what we did is we took the Jade and Jedi data just around the time Juno was orbiting, Juno was at the perigee, closest point to the planet, and then also coinciding with the NuSTAR observation. So you can see 6 different electron spectra from Jade and Jedi. You see some bumps and wiggles due to some cross calibration issues or time variability of electron spectra. But overall, the electron spectra were characterized by a power law model of 1.3 index, which is already hard. So what we did is we shot 100 million electrons downward in a simulation and into the modeled Jovian atmosphere with 80 stratified layers and mostly made of hydrogen, helium, and methanes. And then this is one of the snapshots from the simulation. So red means these downward electrons going to the atmosphere and emitting X-rays, which is in yellow. So what we have done is we figured out where the X-rays are coming from in the atmosphere. So it's actually they're coming from kind of deep in the atmosphere, only 200 kilometers above the surface, where there's ammonia gases located.
2 minutes.
Yeah, okay. Let me wrap up. Okay. Then yeah, these are the simulated X-ray spectra for different cases. So one thing to note is it shows a very flat X-ray continuum in the NuSTAR and XMM band up to 20 kb, and it starts showing some softening above 20 kb. So this is because you start from hard electron spectrum, and then stopping power of the electrons has energy dependence. So that's going to make the electron spectra even harder, and then you get hard bremsstraum X-rays. So this is the final result. So we compared our simulated X-ray spectra and observed spectrum. So again, these are the XMM and the NuSTAR data points, and I put the Ulysses upper limit here. So we were able to reproduce the flatness of the X-ray spectrum up to 20 keV and roll over, and then it's also consistent with Ulysses upper limit. And this is a very robust measurement. The only parameter is just a flux normalization. The shape is always about the same. So we are happy to see that our spectrum, starting from the measured Juno electron data, produced the NuSTAR and all the other X-ray results. So to conclude, I think NuSTAR's unique and significant contribution was recognized in the Jupyter community. We gave 2 presentations at AGN meetings, and then again, we had a press release in the end. So this is my last slide. So what's next? We are thinking about NuSTAR TOs when sun emits a big coronal massive ejections. Maybe we can start seeing hard X-ray brightening of the planet. And then just talk about HEX-P. Maybe we can do a variability study with Jupiter, and maybe we can look at Saturn. Thank you very much.
Okay, questions? Maybe I'll just ask one. I wasn't quite sure I understood. There were historical X-ray observations that showed what looked like kind of a thermal spectrum at low energy, and that isn't seen now by XMM. Did I get that right?
Okay. You're talking about this spectrum?
Yeah.
Yeah, so XMM and Chandra do see the charge exchange emission lines below 2 keV, and then very little continuum emission.
Sorry, what is that from? I missed it.
Okay, so the silicon and the oxygen ions are coming from Io, and you have some sulfur ions from the solar wind, and these ions are going into the atmosphere and hitting the neutral hydrogen, atoms and molecules, and then there's a charge exchange. Basically just exchanging electrons, bound electrons from hydrogen into the silicons and oxygen ions. And then once electrons, in the switch to the ions, and then they start de-exciting into the ground state. So that's where you see the line. So that's dominating the soft X-ray emission below 2 keV.
I see. Any other questions? Well, I'll ask one more then. So is this process going on in Earth's aurora?
Yes, that's an excellent question. Yes, from Earth, people studied Earth's aurora for many years, and they detected MEV electrons and ions, and then they also detected non-thermal X-rays, hard X-rays from Earth's aurora. So we found out the same emission particle acceleration mechanism actually works in Earth and Jupiter. But Jupiter's aurora is so much more powerful, you can see from the Earth.
I see. Kristen.
Yeah, hi Kaya, this was beautiful. So you showed these footprints, not just of Io, but of Ganymede and don't remember the last one. So, but they were at the poles, but the planets are on the equator. So is this just a footprint from the magnetic field lines?
Yeah, so the Io footprints, you're talking about this little blob here.
And also Ganymede and Europa.
Yeah. So so these are the directly connected field lines from Jupiter's polar region and the planet itself. So you get some direct channel of particles coming from these moons into the aurora. On the other hand, the majority of the aurora emission is coming from the Io plasma torus, which is so much bigger. So that's why you have more extended emission all over the place.
But is it a similar process than in Ganymede and Europa?
Yes. Yes.
Thanks.
Okay, so I don't see any more questions and we're about out of time. So let's thank all the speakers in the session. So now we're going to switch gears and talk about future missions. And the first, I'm going to explain this session a little bit. So I'm sure you all read your email that had the performance verification target list for XRISM and thought hard about what you want NuSTAR to coordinate with. So we're going to hear about the PV target list and just overview from Brian Williams, and then we're going to have a coffee break, and hopefully his presentation will stimulate discussion over coffee. And then we're going to come back and we want to hear from you. NuSTAR is planning to coordinate. We have committed that in our senior review, some TBD number of the PV targets. Our data will be public immediately. I believe that XRISM data has 6 months proprietary, but at any rate, you should let us know what you think. So without further ado, can we get Zoom going?
So I'm here, Fiona. Can you hear me?
Yes, Brian, great. So yeah, you can share your screen and the floor is yours. You have 25 minutes or so, and I'll give you a warning.
Okay, great. Sounds good. And you can see my slides?
Yep.
Cool, thanks. Well, I hope I stimulate a lot of discussion. Let me see if I can move. I'm trying to move the participant window out of the way. Is that okay from your end?
Yeah, it looks good for us. We
Okay,
just see
great.
you. We don't see everybody else.
Good. So yeah, I'm going to give a brief overview of the mission itself. And then I'll talk about the PV targets, and I'll talk about some of the things that our science team has come up with in terms of ways that we might coordinate with NuSTAR. So I made this slide years ago for a public talk, but it still works pretty well. I always use it in any introductory talks that I give for XRISM. The name of the game with XRISM is high resolution X-ray spectroscopy. I think most people are familiar with that. An example of this is here on the top left, we have an image of a Chandra image of a supernova remnant, and then the Chandra spectra on the right. So obviously Chandra gives you the high resolution imaging, not so much on the spectroscopy side. With XRISM, we sort of occupy the other end of parameter space. We're not going to make, super high resolution images. We have about 1.2 arc minute resolution, but we will do very high resolution spectroscopy. And you can see here, it's roughly a factor of 50 or more difference in spectral resolution between the CCD spectra that you get from Chandra and XMM to what we will provide with XRISM. So a quick overview of the mission. I think most people are probably familiar with this now, but a really brief one-slide summary is that this is a JAXA-NASA collaborative mission with ESA participation as well. We have 2 instruments on board. Our primary instrument, the one that we expect will do the most science, is Resolve. That is a soft X-ray spectrometer. It's about 3 arc minutes on a side with 30 arc second pixels and 1 arc minute resolution that will do high resolution X-ray spectroscopy in a non-dispersive sense. The other instrument, though, is a wide field imager. It's called Extend. It's about 40 arc minutes on a side, again, about 1 arc minute resolution, and it'll have substantial field of view for observing things simultaneously with Resolve. The Resolve field of view falls within the XRISM field of view, so you get both of them simultaneously. We are scheduled to launch in the spring of 2023. I hope by this time next year we're up and operating. Of course, the mission is to recover the science that was lost with the demise of Hitomi in 2016. And after a 9-month calibration and PV phase, which I'm going to talk about here, the rest of the mission lifetime will be for geo observers. So I think, again, most people are familiar with what happened with Hitomi. I won't go through that in detail. We were lost to an operations mishap on day 38. But prior to that, the mission had been working perfectly. It was even exceeding all of its performance requirements. We only had a few weeks of observations. We were not calibrated. We weren't commissioned or fully turned on yet. But we still had about half a dozen science targets that we got some data from. And last time I counted, there were about 13 scientific papers that came out of this. This was truly a glimpse, and I'll show a result in a second of the power of high resolution X-ray spectroscopy and what we can do in this new era, this new parameter space that we are trying to open up. We do believe this is a transformational leap forward, and this will be the future of X-ray astronomy, is to do not only high resolution imaging, but spectroscopy as well. This is a optical image of the Perseus cluster. If you change over to X-rays, you see something that looks more like this, where you're really seeing all the hot gas that's sloshing around in the cluster. And our most famous result from Hitomi that I'm sure most people have seen is we got the spectrum of the Perseus cluster. This is not what we think the final spectrum from resolve will look like. We'll actually have a lot more response at low energies here. And I'll show an example of that later, of what we expect the full spectrum to look like when we get up to full power with XRISM. But just from this Hitomi spectrum, we can see the obviously very prominent K alpha line of iron out at 6.5 keV. And in fact, when we zoom in on that, this is a very famous image. This is from our Nature paper in 2016. This is the iron K alpha line complex. The blue line that you see is the previous best spectrum of this. That was from Suzaku, where clearly you could see there was a bump there, and you could, obviously fit that with models to the iron K alpha line. But if you dial up the resolution by a few orders of magnitude, you see this, where we're actually resolving the individual components of the lines. The little purple curve there actually shows our spectral response. So the fact that the lines are broader than that means we actually were resolving the widths of those lines. We got a line width of about 165 kilometers per second out of this. And we showed with this that the pressure due to turbulence in the hot gas is substantially less than the thermal pressure of the hot gas by quite a lot. One of the great things about the way the detector works is that we're so cold, we get down to 50 millikelvin, that we essentially have no non-X-ray background. Our best estimate here is that in this part of the spectrum that you see right here, there are something like 21,000 counts. We think only about 16 of those counts total were due to background. So we're really just picking up X-rays from the sky and almost nothing else. We can make rudimentary images of this. This is actually a redshift, blue shift map of the Perseus cluster. If we just looked at the redshift and blue shift of the iron K alpha line. So you can sort of see that you sort of get a picture of the 3D motion here as well, where the stuff in the blue up in the top right, that's coming towards us, and the stuff in red is moving away from us. This was an image taken from a public press release, which is why if you can see the image or the units up there on the top right, they're in kilometers per hour and miles per hour, but I'll leave it as an exercise to you to convert that to actual physical units. So I won't talk too much more in this talk about the other science we can do, except to say that there's a lot of it. We put out a white paper a few years ago. This was around the time that the Decadal Survey was collecting white papers, but this was actually not an Astro 2020 white paper. This was just something that we put out on our own. It may be too small for you to see the table of contents there, but we broke it up into just about every area of high energy astronomy. We cover just about every area you can think of. We even have a small section on exoplanets. So I encourage you to go check this out. We tried to write this white paper in a readable form. It's only about 30 pages long. We targeted it for the general astronomer, not necessarily a expert in X-ray astronomy. But you can find this on ADS if you search for XRISM Science Team. It's also on AstroPH. It's also on our website. So back to the Hitomi spectrum, there are actually two things that I want to add to this. One is that, as I mentioned earlier, on Hitomi, we had not yet opened a huge blocking filter called the gate valve that we had in front of the detector. That was part of the commissioning plan. We just hadn't gotten to that step yet. If you were to open the gate valve, the spectrum would look something more like this. And if you note here, the iron K alpha line out at 6 keV is about the same because we have about the same response out there, but we pick up orders of magnitude more soft X-ray response. So I'll just show that again. This is the actual data from Hitomi, and we just die off below 3 kV. There's no response down there. This is a simulation, of course, of what we expect to see with XRISM when we have the gate valve open and when we're fully up to speed. There is, of course, another major difference between Hitomi and XRISM, and that is that on Hitomi, we had 4 instruments. We had the soft X-ray spectrometer and imager. We also had a soft gamma ray detector, but we had a hard X-ray imager as well. That was never turned on. In fact, extending the boom was part of what caused the operations mishap that caused the mission to be lost. In order to rebuild XRISM as quickly as possible, the decision was made to remove the hard X-ray imager and the soft gamma ray detector. So we're not exactly a rebuild of Hitomi, we're actually a slightly scaled down version of it with just the soft X-ray instruments on board. So if we don't have a hard X-ray detector, and we know there's a lot of great ideas out there for probe missions and things that can replace the hard X-ray capabilities. But as of now, and in the foreseeable future, NuSTAR is going to be the only game in town for doing hard X-ray stuff. And so we feel it's important as a science team to maximize the collaborations between our 2 missions. So I'll give you a few examples of what I mean by that here. And as Fiona said, I hope that this sparks discussion on the various ways that that people think that the synergies can be maximized here. So I want to briefly go over how we selected the PV targets. The PV phase PV stands for performance verification. It's the first 6 months of observations after commissioning. We think that commissioning and calibration will take 2 or 3 months. So roughly months 3 to 9 or so will be the PV phase. These are proprietary to the science team for a year. However, I have a slide later on about the guest scientist program that I'll talk about briefly. We ended up choosing about 55 targets. 35 or so were A priority, which means we will observe them no matter what. 20 or so were C priority, which means we'll observe them if the schedule allows. But if we don't get to C priority targets by the time the PV phase ends, then we will not observe those, and those will be eligible for GEO proposals. The selection process itself was an internal proposal and review process within the science team. It took us about 18 months to do this process. Much of that was slowed due to COVID. Because we started the process when we were still able to get in person, but not long after that, COVID hit and everything had to be fully virtual. So basically what we did was we organized into 4 category teams: compact and diffuse sources within the galaxy or the nearby satellite galaxies, and compact and diffuse objects in the extragalactic universe. So basically the team members went off and wrote proposals for whatever they wanted to write. These were reviewed by the science management office of the mission, which is about 20 some odd people, various chairs of various working groups and things like that. We then gave feedback on all the proposals, and they were allowed several months to go back and edit, expand, rewrite those as necessary. We then had a second round that was due in 2020. These were again reviewed by the science management office, and then we had the longest TAC I've ever served on, partly because due to time differences, we could only do it for about 2 hours a day. We met once a week for several months to narrow down the list and come up with the final list. So these final selections, which I'll show in a second, have actually been public since February of 2021. I would imagine a lot of you have seen them. If not, I'll give you several websites in a second where you can go and look at them. We have just recently, though, added science objectives and brief observing descriptions to all of these PV targets. So if you go to the web page now that I'll show in a second, you can actually click on every target and find a brief write-up from the science team on those. So these are the various websites. There are websites in Japan, Europe, and the US. For US folks, if you're going to the NASA site, we have 2 NASA sites. There's more of a public-facing site that's meant for the general public. The researcher site, though, can be found at the link to the bottom. And of course, these sites link to each other. So I'm certain you all can Google fairly quickly and find the researcher site for XRISM that has things like response files, software for download to analyze XRISM data, all the stuff you need for that. So I'm going to briefly show all the PV targets. These are literally just screenshots from our website. So everyone should have seen this by now. The first up is the galactic compact PV targets. So these are, of course, when we say compact, we really mean point sources. These are point sources within the galaxy. So you'll see a lot of your favorite targets here. You'll see a lot of the famous X-ray binaries. You see things like Eta Car. We've got a few flare systems here. I guess as Cygni. T Corona Borealis is a white dwarf. If we move on to the galactic diffuse targets, now we're looking at more like the supernova remnants in the galaxy. You can see all of your favorites there. There's SN 1006. There's 87A in the Magellanic Clouds. We also include in here a few other things like the galactic center. So we're going to have several pointings at the galactic center and just off. We also have a few, the GX13 and GX340 targets. Those are dust scattering halos surrounding bright point sources. So that's why these fall under the diffuse targets. And in fact, if you go back for a second, you can see GX13+1 is a compact target as well. So the idea here is we're going to observe both the bright X-ray source in the center and the surrounding dust halo of X-ray scattering coming in from a few arc minutes off source. We are also going to try and observe a comet. We have a few candidates that we think will be visible within our PV phase. And of course, we have a lot of priority C targets here as well, including Jupiter, as we just heard a talk on Jupiter. We are going to try and observe Jupiter. We're pretty sure we can do this. I meant to point out earlier, but I forgot. Our preliminary scheduling simulations show that we expect to get something like 75% of the priority C PV targets scheduled. Moving into the extragalactic compact, we see a lot of our familiar favorites here, the AGN. There's NGC 1365 and MCG 6. So obviously a lot of familiar targets here. And then moving on again to the extragalactic diffuse targets, we have a lot of the clusters. So again, all familiar targets, all ones that you can go online, click and see what it is we're actually planning on doing. I'm going to now show the target list again with a modification. The numbers you see in red here are the numbers that the XRISM science team has gone off. We asked them to go off in your individual target teams and think about what joint observations you think would be necessary to achieve science above and beyond what was written in the PV proposal. So what I mean by that is we instructed the science team to only write PV proposals, not assuming any joint science observations. Assume XRISM is the only astronomical mission that's flying when we launch, and write up good science cases for that. But afterwards we said, okay, now that you've done that, if there is additional science that you can do with joint observations with NuSTAR or NICER or SWIFT, what have you, write those down as well and give us numbers. So I'm sure it'll come as no surprise that NuSTAR was the most requested instrument for joint observations with XRISM. There's just a lot of science that can be done with adding in the hard X-ray spectra to the soft X-ray spectra to really constrain the models. So I'm not going to go through these all in detail. That would take far longer than I have. I'm also not an expert in every single PV target. I will point out a couple of them, though, of interest. The first two here, this is the galactic compact group. Again, the first two up on the left, 4U 1916 and 1624. These are low mass X-ray binaries that we call them dippers because they show a periodic dip in their light curve. So our plan with XRISM is we're going to observe, we have 50 kiloseconds there for each, but that's really 2 times 25 kilosecond observations, one in the dipping phase and one in the normal phase. So the request here from NuSTAR would be to kind of do the same thing, although the simulations show that it could be slightly shorter. So two 20 kilosecond observations of both of those. For some of these others, you can see again the familiar targets. I don't have details behind each simulation of why it was, why is this 50 kiloseconds, not 75? I don't know. But you can see that most of these targets in the galactic compact group, our science team feels that it would be beneficial to have NuSTAR observations. In general, we would prefer those as simultaneous as possible. Of course, we realize that that may not be possible due to scheduling. So we will happily work with the NuSTAR team and the XRISM team schedulers to see what is possible. So moving into
5 minutes.
galactic diffuse. Okay, great. In the galactic diffuse, there was not a lot of request for NuSTAR time. So I'll just move on past that to the extragalactic compact, which had every single target. The science team or the target team for that target felt that joint NuSTAR observations would be very much of interest. A few of these have double asterisks by them. That simply means that these are not necessarily required to be fully simultaneous. And in fact, there are various ways that we could schedule around that. The others are, to the extent that simultaneous is possible, that would certainly be preferred. So again, these are mostly the AGN, but these are all targets in which it was felt that NuSTAR time would be useful. The extragalactic diffuse did not make a request. So if I added up all of the times that I just showed you, the total request time for NuSTAR coming from the XRISM science team was 1.1 megaseconds or thereabouts, 1.1 megaseconds for the priority A targets and 0.6 megaseconds for that's a typo, that should say priority C targets. So with that, let me just throw up a few last minute slides here on other things. There are other ways to get involved with the XRISM PV phase targets. We have something out called the XRISM Guest Scientist Program. This is where anyone who is not on the XRISM science team can apply to join specific targets. So if you are super interested in target X, you can write a proposal to join that target. The AO is open right now. In fact, the due dates are kind of coming up rather soon. There are 3 separate solicitations, one from NASA, one from JAXA, and one from ESA. The NASA one is due July 21st. The JAXA and ESA are both due much sooner than that. They're due on July 4th. I encourage you to go to the web, go to our website. We have plenty of information on that, on the process for applications. I just want to point out that you don't need to be an expert in X-ray astronomy to apply to this. We are seeking out people with any sort of complementary expertise to that we already have on the science team. Lastly, I just want to point out that, again, after the commissioning and PV phase, the remainder of the mission is GO. We will operate like every other mission out there, Hubble, Chandra, NuSTAR, et cetera, with an annual call for proposals. This will be done simultaneously between JAXA, NASA, and ESA, and you should apply to the appropriate one, which is based on where you are currently situated. So if you're at a US or Canadian-based institution, you'll apply to NASA. If you're in a European member state, you'll apply to ESA, et cetera. We think that AO1, our tentative schedule has AO1 coming out about 2 months after launch. So if we launch next spring, that's going to be, summer or so, with a due date 3 months later. And then we expect that AO1 will commence in early 2024. This is sort of NASA specific. I apologize if that's not relevant to everyone, but on the NASA side, at least for anyone at a US institution, we have a total budget of about $6.5 million for cycle 1 observations. We're trying to reserve about $500,000 of that for laboratory astrophysics. And so we'll have more information when the AO actually comes out. But if you are a laboratory astrophysicist or a theorist who wants to do simulations, we will have some money set aside for either theoretical or experimental laboratory astrophysics. Lastly, we're going to have something called the Early Release Science Program. And this is so that people can be as well prepared as possible to write AO1 observations or AO1 proposals. We are going to release a few observations very soon after launch. As soon as we feel confident that we're commissioned and turned on. Notice I did not say calibrated. This may be pre-calibration data, but we'll get it out as soon as possible so you can at least see some data from the telescope before you have to start writing your AO1 proposals. So we'll do our best on that to get it out as quickly as possible, and that'll be totally public. So I'll just end with this again. I'll put up the 3 websites here. All of these have the entire list of PV targets. So again, I hope this will stimulate some discussion, and I'm happy to take any questions about this. Thank you.
Great. Well, we're definitely looking forward to your launch. So why don't we take 5 minutes for questions about the mission, and hold your questions about the PV targets for after the coffee break. And I'll read one off of the chat, and then Javier has a question. So from Poshak, what's the best spectral resolution achieved in ground tests for the microcalorimeter?
Yeah, our ground tests are a little less than 5 eV. I mean, it's the design has been perfect so far. We're getting something like 4 eV on the ground. Our mission requirement is 7 eV on orbit, so we think we're very much in line to achieve that. If you recall, on Hitomi, we actually measured 5 eV on orbit, and we had virtually the same ground test there. So everything's going very well with the calorimeter integration and testing. We're very happy with it.
So Poshak wants to know if that's at 6 keV.
Yeah, I mean, it's close to that. I think it's like 5.9 or something. But yeah, it's basically there. Yeah.
Okay, let me just check the chat. Go ahead.
This is just a really basic question, but what does AO stand for? Clearly, it's not adaptive optics here.
Announcement of opportunity.
Okay.
It's just a call for proposals, basically.
Okay. Anybody else? Javier, did you have a question, or you? Oh, it's about the PV targets. Okay, so hold that for after coffee. Any other questions? Well, maybe I'll just ask. So where is everything shipped at this point? Being integrated in Japan, or?
Yeah, actually, I'll tell you what, I don't have it handy, but if you take a break for coffee, I'll show you a picture that we've recently released publicly so I can show it. The Resolve instrument has been fully integrated onto the spacecraft. So the picture I have, you can sort of see the instrument inside when the spacecraft is standing up. The mirrors, both the XMA is X-ray mirror assembly 1 and 2. Those are identical mirrors, one for Resolve, one for Extend. Those are both built and calibrated at Goddard. Those were both shipped out about a month ago. So they are both currently in Japan. They're undergoing integration and testing there, and will be integrated onto the spacecraft in the next few months. So yeah, we're getting close. Like I said, when we come back from coffee, I'll show you the public photo that we just put out last month.
Great. So with that, why don't we? I'm sorry. Go ahead.
Sorry.
Yes. Yeah.
Hi, Brian. Victoria here. I was wondering about, well, I hope it's not a PV target question. How simultaneous would the observation with NuSTAR actually be? Because both of them are in a low Earth orbit, right? So some of the sources have visibility gaps. So is there kind of like a basic answer to this question, or does it really depend for each individual source on the details of the scheduling?
I think that's a great question. I don't know the exact answer to that now. I mean, obviously if there are scheduling constraints that we can't get around, then there's nothing we can do about that. So we'll have to do the best we can. There are some targets where the target teams have said simultaneity is not required. There are some targets where the target teams have said even just a slight overlap would be useful. You know, if XRISM is doing 100 kilosecond observation or something, and NuSTAR can overlap for the last 10 or 20 kiloseconds, that would be fine. Some of them would like as much simultaneity as possible. So I think that's going to have to be a question that when we know more about our launch date and when we actually get on launch and have a long-term schedule, we'll have to have conversations between the schedulers for both missions.
Okay, I guess I may have asked it a little bit wrong. So what I was worried is less whether the kind of like 100 kiloseconds over the 100 kilosecond parts overlap, but about the gaps you have because of the low Earth orbit, right? In each observation. So what happens kind of like how much overlap there is in those gaps or in the actual observational time?
Yeah, so I think what she's at, we won't know till we know the final orbit insertion.
Yep.
How and it'll also obviously depend on where in the sky the target is, because some are in continuous viewing zones, some are maximally occulted. So I think it's
case by case. Okay, thank you.
Yeah, it's going to have to be case by case, and our orbit is different too. I mean, we're launching in a 31-degree inclination orbit, so we have a continuous viewing zone, but we're also occulted a lot. When I know NuSTAR, I think you all are in what, like a 5-degree orbit or something like that. So it's not exactly the same. So it's going to have to be a case by case basis, though.
right. Well, over coffee, you can think about the orbital geometry that you want and then request a particular launch time as an exercise. Okay, great. Well, thank you very much. Let's thank Brian again, and we'll come back. And come up to the mic if you want to start discussion on any topic, and Dom can come up and ask why there aren't ULXs on the list.
Well, I'm gonna ask, is there a priority list within the priority list? I mean, the 1.1 megaseconds is a lot for NuSTAR to cover in 6 months. So is there an additional priority list under the priority list to whittle that down if we say this is not going to be doable?
There's not yet, but we are willing to have that discussion. I mean, Fiona may recall when we first chatted, I don't know, 6 months or maybe a year ago, whenever it was, that was something we chatted about then, was, if you come up with a list and that's just not feasible, can we prioritize there? And the answer is yes, we can. We haven't done it yet, but that's something that we need to have at the project level, NuSTAR to XRISM, to say, what is a reasonable amount of time that you all can cover within the PV phase. And if it's some number that's different than what we have, then yes, we would prioritize. And that would also be dependent on scheduling as well, as we get closer to launch and have a more firm launch date. So it's not, the answer is not yet, but yes, it's possible.
Yeah, and so if you want to speak up, anyone in the audience wants to speak up for things that really have to get done with NuSTAR data, then that's part of this discussion. I mean, the challenge, it's 1.1 megaseconds roughly, but it's all within 6 months. And so it's sort of, since it's concentrated, we'll have to see, it would be good to have priority, some kind of prioritization. Greg?
Yeah, I have a quick question. How large of a team do you expect for each target? In other words, how many people do you think will get accepted from those who are proposing?
So I assume you're asking about the guest scientist AO, and within.
No, I'm asking about the proposal that is coming up for the PV target teams.
Oh, well, so within the XRISM team, the target teams have already been formed, and they are anywhere from 3 or 4 people for some targets up to 12 to 15 people for some other targets. As far as adding external folks through the guest scientist program, we will add on average 1 per target, but that is very much an average. There will be some that have none added. There will be some particularly high profile targets where obviously we're not going to just limit it to 1 person being added, so we might add 2 or 3 people for that.
Okay,
but on average, we expect, of the 50 or so PV targets we have, we expect to add 1 per target.
Okay. Why don't you say your name so Brian can know who's asking the question? Oh, I see. We also have hands raised, so good.
Yes. Hi, Brian. This is Nazma. So the ROSA solicitation that came out for the XRISM guest scientist position does not mention if the guest scientist would also have access to the NuSTAR. Like, do we write the proposals also including the proposed NuSTAR observation, which would be simultaneous with the XRISM observation?
My recommendation would be not to, only because that hasn't been firmly ironed out yet. I would advise the same thing that we told the XRISM science team when they wrote the PV proposals in general, is that write your proposal assuming that XRISM is the only thing in the sky. And if you want to add to that and say, you know, in addition to that, if we get NuSTAR data, we can do this, this, and this, that's fine. But I would not advise writing a proposal that only says, you know, only if we get NuSTAR or NICER or SWIFT or whatever, can I do this potential science. I think that was the second part of your question. Was there a first part or was that the whole thing?
No, this was the whole question, but it's like the science that I'm proposing with XRISM. Can we make statements like if we have the NuSTAR data, it would complement or give certain significant constrain certain properties more, or we only stick with XRISM observations and make statements on that?
I think it's fine to say that. I think it's fine to say if you have additional data, we will do additional science, but I just wouldn't make that the primary focus of your proposal.
Okay, thank you very much.
Okay, Poshak, you're gonna start us off.
Okay, thanks, Fiona. So I guess in addition to the listed targets, there is also a provision for a small number of target of opportunity or potentially DDT observations to be performed during the PV phase. I would recommend that, of course, those should be obvious targets for coordination because it's a no-brainer. But I guess, is that a separate discussion or should we be discussing that here? Should we write separate proposals for that?
I think that's a separate discussion. You know, it's allowable as far as I'm concerned to write a proposal for that. I don't see anything in the solicitation that disallows that. Obviously, it's risky.
Sorry. I guess that was more. I guess that was a comment more for Fiona, as in should we be writing separate NuSTAR DDT proposals for that? I guess.
Okay. Well, I will defer to the session chair then.
Yeah. Oh, I see. Well, so maybe you can tell us what are the I mean, during the PV phase, are you going to do TOOs or you know, what is the TOO policy in general? Even is there going to be director's discretionary time? Is it all going to be through AOs?
So there is a small amount of, sorry, Brian, you should answer.
Okay, so during the PV phase, yes, there is some amount of director's discretionary time. I mean, we always sort of say that, you know, if the next galactic supernova goes off, we're going to have some mechanism by which to allow time to observe that. We do have a few targets that were proposed during the PV phase that were approved, but they are only if they happen. So nearby supernova would be one, nearby bright tidal disruption event, a nearby emerging black hole event. It's a gravitational wave. So we have those, we sort of have those in the potential schedule, but I hesitate to even schedules because, you know, obviously there's things that we don't know if they're going to happen.
Yeah, so I guess my answer from NuSTAR would be if XRISM triggers a TOO during the PV phase and somebody feels that NuSTAR data is important, then put in a DDT request. Because we do take DDT requests for coordinated observations. Just don't make it 48-hour turnaround. So. Okay, so we have online Pragati.
Yeah, hi. First of all, thank you for doing this. I think it's a great idea to bring both the high res and the hard X-ray spectrum together. I especially work on X-ray binaries, so for me, both the aspects is important. And we've been thinking about this simultaneity, XRISM and NuSTAR on individual levels, and I've led a proposal on actually observing a PV target list with XRISM, the one Brian was mentioning for your 1624 with NuSTAR, and that got accepted in the last cycle. So that was in cycle 8, but I guess that will not be simultaneous with XRISM. Nonetheless, it will give us an, a non-simultaneous first NuSTAR observation of the source. My question was, when Brian was actually showing the PV target list, there were a couple of sources where the NuSTAR observations were not like, they were not requested, or is there a specific reason, or did the team feel like it's not needed, the hardware spectrum is not needed to achieve the science goals with XRISM?
Well, I can't speak for every individual science team. I mean, or target team, I should say. There were about 55 different teams with overlap, a lot of overlap between the science team members. I will say we asked all of them to consider what joint observations they might require. And of course, there are other observatories as well. There were some that said, we need periodic monitoring with SWIFT or NICER or something to see when it goes into outburst, but it was less important to have NuSTAR or whatever. So the list I showed you, where I showed where I had all the red numbers from NuSTAR, that was NuSTAR specific. There are a lot of other things where, periodic monitoring would be important. So I can't say that it's not important to have NuSTAR, but some target teams felt that it was not as important, or another observatory was more important. So I think that's the best way I can answer that.
Okay. Sure, got it. Thank you.
I mean, in an ideal world, of course, we would observe every target with every instrument, and we would all, do everything we wanted to do, but that's obviously not possible.
Yeah, so I think then this goes back to what was mentioned by one of the participants, that if we think that, NuSTAR, because I can already think of a couple of cases where NuSTAR is going to be useful in along with XRISM, and that was not there, and that's one of my favorite targets, so I thought I'd bring this up. So maybe one of the ways to approach this will be, maybe mention a couple of lines in the XGS, the guest observer, and see where it goes.
Okay.
Yeah, sorry, I'm not sure I understood that. Was that a question? I'm not sure I understood the question.
No, I'm saying, so maybe one of the ways to make sure that the XRISM and the NuSTAR kind of looks into the target that you think is important like in terms of the simultaneity or observations between XRISM and NuSTAR. One of the ways to give an input is maybe write it in the guest observer program, a couple of lines saying that, okay, maybe if NuSTAR observes this, and this is one of the ways to go about. I mean, because right now at this point of time, I, not being in the XRISM team, don't have a way to give input. So the guest observer is one of the guest scientist program is one of the way I can provide input probably.
Okay.
Okay. Well, I will ask a question since and Dom's getting up to ask about ULXs, I can tell. So I noticed SIGX1 was on the list, and I think it's fairly obvious why NuSTAR would be useful. But I was under the impression there were count rate limitations for XRISM. Is that incorrect?
No, that's correct, but we are actively looking into ways to mitigate that. So we're coming up with a lot of different strategies to overcome bright sources and still do observations of those. We have some ideas of how we'll do that now before launch. Some of those will obviously wait till we're in launch and we actually try some of these things out. But we have, within the science team, we have a working group called I think it's just called Bright Sources Working Group, which is trying to come up with mitigating strategies. And of course, this will of course be a thing that evolves over the mission. We'll try some things, we'll learn something, we'll go back and develop a new strategy, but there are limits. Of course, we can't, we would just completely lose resolution if we pointed at, the brightest X-ray sources in the sky. But we're working on that. And so at this point, we're saying that every target is still theoretically feasible.
Okay, Dom.
We actually switched around because
Oh,
you
okay.
mentioned, sorry, but you mentioned signal 6.1, and I had a question about that, maybe also in general about the approach. So one thing I've seen is that it's 100 kilosecond XRISM observation, but only 40 kilosecond NuSTAR observation. Some science goals can of course be addressed with that. But if we think about also creating an amazing archival data set that in the future can be reused for other purposes, this is a source where I would make an argument that having full simultaneity, or at least 100 kilosecond, given its variability, would make sense. I guess my question is, where the requests driven by specific science goals of individual data sets, or where the requests for NuSTAR time also driven by the thought of creating kind of like an archive, kind of like for the future, a legacy that can be reused. And then I would argue, maybe we should add a little bit. I know signal 6.1, my favorite source. Sorry about that.
Well, again, I can't speak for every individual target team. I certainly wasn't a part of 50 plus individual discussions, but my guess is that most of them are motivated by science, immediate science results. But I certainly understand your point about creating an archival legacy for both of these missions. And if it's possible to do, longer observations with more simultaneity, that's also something that could be done in the geo phase. If we're not able to do that in the PV phase, we have an entire geo phase available for that as well, as does NuSTAR going forward.
Yeah, I mean, I guess I'll make a comment. I think it's a good point. And I think when we're discussing, what NuSTAR is actually going to do, I would suggest communicate with us because, you're right. It would be a legacy data set. And I'll remind you, the NuSTAR data will be public right away. And I think the PV data is 6 months. So
PV is a year. 1 year.
It's a year. Oh, okay.
It is, yeah.
But
All right.
honestly, from my personal experience, it may be a data set that people will work on for the next 10 years.
Yeah, no, I think that the part of this discussion is this data is all going to be in the archive. And if there's something you think that we should, that's not listed as joint NuSTAR that you think we should do because you think it would help your science when it's all public, and that's the kind of thing we want to hear about. So great.
Hey, Brian, it's Dom. I'm actually not going to ask about ULXs, although Fiona was probably not too far off the mark. My question, I guess, is regards to the early release science observations. How are these targets going to be selected? And is the coordination with NuSTAR going to be considered in light of that, given what we just heard about, with the NuSTAR data being public immediately? Is there an expectation that observations that are coordinated with NuSTAR would be more likely to be selected for the early science release program to sort of match that data release policy?
Yeah, so the NuSTAR nor any other joint observations will be considered for the early release science stuff. These are going to be targets that, as we get closer to launch, we're going to try and pick out a couple of targets, sort of a representative sample. We are not going to be taking these from the PV target list, and we're not even planning on taking them from the PV targets that were proposed but not selected. For lack of a better word, we're going to try and choose the most boring targets in the sky that we can think of, because we're not trying to step on anyone's toes of, oh, this would be my favorite AO1 proposal target. We're going to try not to do that. So we're going to try and just come up with a generic example of here's an X-ray binary, here's an old diffuse supernova remnant or something, and just here's a couple of examples of what the data is looking like as we get them. So hopefully that makes sense.
Sorry, might the IR check suggest you pick some of the calibration targets? I guess you're going to do some anyway.
We have an entire in-flight calibration plan,
right,
yes, that we are coordinating through, and the early release science targets are also not going to be calibration targets.
Well, and when will the calibration data be made public?
I don't recall that off the top of my head. I mean, it will certainly all be made public eventually. I don't know if the plan is to make that public right away, but we will certainly make available whatever we feel is necessary for people to be able to analyze and reduce and understand their own data. But I don't recall. I could try to bring up the policy documents that we have regarding calibration data, but I don't recall if that's planned to be made public immediately or somewhat later.
Okay, go ahead. Yeah.
Okay, that's actually following. Hi, Brian. This is following up on that a little bit. So analysis tools, are you thinking of maybe having some workshop? Because you said that some of the observations are going to be public so that us who are not on the team can kind of play around with them. But if we don't know what we're doing, then we're not going to learn anything. So do you plan on having, through that first year when you're busy doing your analysis, perhaps some workshops to help the community kind of, not struggle when, go ahead, please.
Yeah, absolutely. I'm glad you asked that. So we are currently in the preliminary stages now of planning our first data analysis workshop, and this will be pre-launch. I don't have a date yet, but we're likely targeting early 2023. And this is something that we will do on a regular basis. We'll do at least one pre-launch. We'll probably do another one a few months after launch. And I envision this being in every regular interval. I don't know if that regular interval is every 6 months or every year, or maybe it changes, but yes, absolutely. We're going to host data analysis workshops for the community to come in and learn how to use our analysis tools, how to interpret the data. And we're working on some analysis tools now. I mean, we have all the standard F tools that have been around from the HESARC for a long time, but we're even developing some new things. We're developing a GUI for analyzing spectral data, sort of a point and click. What is this line? What is this line? What's the width here, there? So we have a lot of things that are going to be coming out relatively soon. And yes, we will. It's a major goal of our guest observer facility to train the community on how to use these things.
Fantastic. Thank you.
Brian.
Hey, Brian. So I was actually maybe going to target the people in the room a little more. So, this week we've heard a lot about, the sort of real fundamental, we looked at NGC 1365 and there was a debate that was put to bed by the fact we saw the relativistic reflection and not partial covering absorbers. So if I'm looking at the AGN list here, I sort of went through and I looked at the abstracts and I picked out some things that certainly they're supporting science that's there, but maybe for the people in the room who can, really think about if there's one or two. I think I agree with Victoria that SIG-X1 is a great archival data set. SAJ-STAR makes absolute sense. A lot of the AGN targets, I'm trying to figure out what is absolutely essential for NuSTAR to do amongst those, as opposed to things that it would just be nice to have. Maybe I'm trying to be a little provocative, but.
Okay. Yeah, I think maybe it's a little abstract at the moment for people. But, since we only have 1 minute left, what I'm going to suggest is that this, hopefully stimulated you to go look at the PV list and think about it. Email me or anyone on the NuSTAR team if you have thoughts about, gee, it seems to me the XRISM team doesn't have this source listed as joint NuSTAR, and here's the reason why it should be. Christine.
Well, I just wanted to, should we arrange a series of not workshops, but meetings where people can join in and we can talk about some of those things now when they've had time to look at the list and think that over, maybe in a month or 2 months. What is our deadline for this, from these decisions?
Well, I mean, from the NuSTAR point of view, I think we need to know roughly how much we are going to do before the AO release that would coincide with the PV phase. So it sounds like that's the next AO, right? Because
So that would be spring 23.
yeah, because as you point out, if we're concentrating over a megasecond in 6 months, then that'll we want to advertise that we're going to select less, geo.
Right, we would have
targets.
to take
What-
it away from the geo program.
Yeah, we have to, or take, do something TBD. So yeah, I think
the deadline it's September, right? Because we have to, the AO comes out,
Right.
we submit things in January. So if we want to adjust the NuSTAR AO, it's got to happen in the next month, right?
Yep, that's right.
AO releases in October. I guess that's Carl. Yeah, I was thinking, yeah, so the AO cycle or the cycle starts in spring. Right?
Yeah. So this is timely. And so I think we're out of time, but thanks for joining us. And we're all really excited to see the data from XRISM. And I think Christine's right. What we'll do is those people who are interested, we'll kind of set up a Zoom meeting where we can go through the list and people can make suggestions, and it'll help us filter on our end. So thanks very much. And I think with that, I'm going to hand it over to the HEX-P session. So thank Brian again.
Okay, thanks. Thanks for having me here. Happy to join.
So we are now moving way into the future, maybe not as far into the future as you might think. And we're going to talk about the high energy X-ray probe. And because we are here in Europe, where probes and the decadal survey. You can't hear me? Okay, here, I'll get a little closer. And because we're here in Europe, where probes and the decadal survey might not be as familiar to you, I am just going to talk a little bit about it, just to give you kind of, to place the setting of what the probes are and how they came about. And you have probably already heard a couple of times people mentioning the decadal survey, and this is a big thing in the US. Everyone in the US knows a lot about it, but it might not have percolated over to Europe. So let me just talk a little bit about decadal survey. So it was commissioned by the national academies, and it happens every 10 years. And what happens in this decadal survey is that they solicit white papers from the community. And so the one that happened in 2020, and most of the papers went in 2019, is there were 13 panels, and there were over, I think, almost over 1,000 white papers that were submitted by the community. And then the panels go through the white papers, and they then make recommendation for what's going to be the path in the next 10 years for NASA's investment in the science. And our very own Fiona, who is not here right now, but Fiona was co-chairing it with Robert Kennicott. So she knows a lot more about this than I do. So the decadal survey came out in 2021, despite its name. And so it came out December 2021. So we've only had it for about 6 months. And there were 3 pillars, as you can see, and I can't barely read them, but I'll try. So there was worlds and suns. I can't read. Okay, I have to look up. Worlds and suns in context, which is, as you can tell, it's focused on planets and nearby stars, or stars around planets, and new messengers and new physics and cosmic ecosystems. And you can see there's these symbols at the bottom, and the X stands for X-rays. So pretty much X-rays, so those symbols showed which band in these pillars belonged in these pillars, and you can see that the X appears in every single one of them. So there's a very strong motivation for still having X-ray observatories, and that was supported by the decadal survey. So what also happened in the decadal survey, and this was one of the big questions that the American community wanted to have answers to, and that is the probe class. So pre-decadal 2020, we had sort of three classes of explorers. We have three classes of big observatories, if I'm not counting CubeSats. And these were small explorers, of which NuSTAR is a small explorer. And then you've got the mid-X, the medium explorers, which is something like Swift. And then you had a flagship, which would be Chandra. And you can see that there's an enormous gap between the 200 million from a medium explorer to a flagship. And this is where people wanted to have these probe class, which would be a 1 billion, around a 1 billion. Sometimes they talk about 1.5, but around $1 billion. Which would be a larger observatory that would kind of plug that gap, because it takes years for the flagships. And in fact, 4 flagships went into the decadal survey. One of them was Lynx, which would be the next big X-ray observatory, and it was not picked as the one that should be focused on the next 10 years, which means we will probably not see this flagship, an X-ray flagship, for another 20 to 30 years. So in terms of new big observatories, there is Athena, and for the NASA side, you would have explorers and now also possibility of a probe class. And the way that the probe class was expressed in the decadal surveys, as is shown here, which was actually written by Fiona, is that they recommended that you would have a probe class that would be complementary to Athena. That was how it looked. And very quickly, literally less than a month after the decadal survey came out, the first AO, the first draft AO from NASA, the first draft AO from NASA came out that they were suggesting that we should indeed do probe classes. And their recommendation was that we should have an X-ray probe and we should have an IR, infrared probe. So you may be familiar now with that there is some troubled waters on the horizon for Athena. And so in May this year, NASA removed the complementary to Athena, so that now it was just a probe class, X-ray observatory, or an infrared, and they removed the complementarity to Athena altogether. So there are 4 probe concepts that are in the books or in the works right now. We are all still looking for enough funding to be able to propose. Access is probably the most secure because they're going to come out of Goddard. And you can see, so here, HEX-P. So how do these probes look compared to each other? So you've got HEX-P, which is the broad bandpass with high angular resolution at hard X-rays. This is, if you want to summarize HEX-P, that's what that is. Axis would be high throughput and high angular resolution. So you can think of that as a bigger Chandra. Then you've got StrobeX, which is focused on an array of instruments focused at timing. And so this would be your bigger, nicer version. And finally, you've got LEM, which is a high throughput, high grasp. So big fields of view with a calorimeter. It doesn't really have something that's come before. So LEM is probably the most unique among them and the most specialized of these 4. So we know now, so there is a draft AO that came out also about a month ago. It came out in May. So this is the timeline, and this is what we're all a little bit deer in the headlights, because this is quite fast. We are looking at next year already is when the final AO, which is announcement of opportunity, let's just say that again, but it's a different announcement opportunity. It comes out in July 2023, and then you've got 3 months to make your proposal and submit it. But of course, ahead of that, we're going to have a year to prepare for those 3 months, and that's what we are in. That's what we are going through right now. And so after you've submitted that, you're going to have a down select of X numbers. It's probably something like 2, possibly 3, but most likely 2. So in 2024, they'll pick 2. Those 2 will then go through what's called a phase A. So that's a more extended study. And then one of them will be picked the early well, the reports are due then in early 25, and then mid-late 2025, you will actually have picked the probe. And then the launch is somewhere in the early 30s, or hopefully 30. So you can already see that with the things you know about Athena, even if Athena was not in troubled waters, there's a big possibility that the probes will actually launch before Athena ever sees the sky. Okay, so here's a brief HEX-P overview, just very top level, and it is a larger NuSTAR. It's got a focal length of 20 meters, which is what really gives us the possibility to go to higher energies and also to get a higher effective area. So those 20 meters are very important. And then in terms of the angular resolution, we are using a different type of mirrors than what we had on NuSTAR. So we'll go from 60 arc seconds to something like 5 arc seconds. These are the same mirrors that would go on axis. The reason why we don't have 1 arc second is because we have to put some very thick coatings on and they may distort. So that's why we backed off on something like that. And it also, it's more costly to have 1 arc second. So 5 arc seconds is what we are baselining for. So just about the HEX-P management. So it was a very difficult couple of months for all 4 missions trying to make sure that we had the support, because the NASA centers, there's only 2 NASA centers that are allowed to support these missions, and that is Goddard and JPL. There can be other centers as well, but these were the ones that everyone had to go to, at least in these missions. And we shopped around for a while too, but we can now happily announce that JPL is agreeing to be managing us, of managing the proposal, which is really good, which means we have a very good, we will almost 99% be able to submit a proposal, which is great. The principal investigator is Daniel Stern. He will speak to you a little bit later. I am the deputy PI, and we've got Javier as our project scientist, and he will talk a little bit more about the science team, how we've kind of organized that in a bit. There's a couple of instrument partners. So the mirrors I've already alluded to, they're going to come out of Goddard. It's the same people who did the NuSTAR mirrors. It's just a new type of mirrors, but it's going to come out of Goddard. So much of this is the same as NuSTAR, just bigger, you can tell. Then I have here some acronyms. That's HET and LET, and this is high energy telescope and low energy telescope. So I've already tipped my hand and told you that if you were familiar with HEX-P before, which was just purely hot X-ray, you will be surprised now to learn that there is now a low energy option, but we'll get into that in a bit. So why don't I just do that right away? So we've got 1 low energy telescope, and the reason that we have decided to do that is because we've lost the complementarity with Athena. It would have been fantastic if Athena had flown at the same time as HEX-P, but we could not. With the way it was going with Athena, it was very hard to make the case in the proposal that you would be simultaneous with something like Athena. And the current X-ray landscape, if we look at it realistically, we're probably looking at XMM might survive that far, XRISM probably, but a lot of the others may not make it. Chandra is already burning up from, the sun screen is kind of falling off. And SWIFT is also an aging satellite. So it's very hard to make the case that there will be a low energy mission at the same time as HEX-P. So that's why we decided that we needed to be our own low energy telescope as well to provide that coverage. And we've heard today, a lot of the science is just made so much more competitive and impactful by having the low energy coverage. So what we're envisioning is you have a low energy telescope that goes all the way. It's a regular CCD. Well, we could talk about a different detector, but right now, let's just say it's a CCD, and it has the regular 0.1 to 10 kV. In fact, it actually is much more efficient. If you see in this plot, you can see that red curve that's called LET. That's actually what the effective area looks like of this low energy telescope without having a detector in it. So it has effective area all the way up to 30 kV, and it's enormous. When you throw a silicon detector in front of it, that goes away. So we may look into if we can recover some of that area with maybe a different type of low energy detector. Then at the heart of it, we've got 2 high energy telescopes, which will then go from 2 to 150 kV. And the low part, the 2 kV is decided by the detector type, and the high part is simply the coatings on the mirrors themselves. So here's just in a little bit more detail of what those effective areas look like. So you can see that the low energy telescope is, so compared to an XMM-PN, so this has been folded with every known effect, efficiency, detector efficiency, mirror efficiency, and PSF correction. All of that has been put into it right now. We have some wiggle room, which means we can increase those areas, decrease those areas. There is a trade-off between the low energy, so what's on the left, and the high energy, what's on the right. If you take something from one side, you can shift it back and forth between them. So we have some wiggle room to adjust these effective areas as we start developing our science case and become more confident about what we're going to showcase. So we have already response files ready. They are being tested now. And once they pass their test, we will make them available on our webpage, which is HEX-P.org. And with that, I think I'll stop and I'll take questions before we move on to Javier, if anyone has some.
What orbit is the mission planned?
Sorry,
at?
what?
Which orbit will the mission be at?
Orbit. Okay, which orbit will the mission be in? That's a trade we have to look at. For background, NuSTAR is in low Earth orbit, and for background, you may say that, but with NuSTAR, we are actually experiencing a lot of near collisions with small CubeSats. So there might be, not just because of having more continuous viewing in a high Earth orbit, there's also maybe a reason to just get out of low Earth orbit, not to get knocked down by someone's little CubeSat. But this is a trade we're still looking at. But if there is a desire from the team that we really should have more continuous, then please voice it, and that makes high Earth orbit or a lunar cis orbit, which someone has suggested as well, might be attractive. I can't see if there's anything on Zoom.
They were complaining about there was a problem with the slides. They couldn't see everything, but there are no questions.
They couldn't see our slides.
I'm not sure I understand what the problem is.
We can see most of this slide. There's just like a little blacked out section. at the
Okay,
bottom.
okay, you saw most of the slides. Okay, well, in that case, let me hand it over to Javier.
Okay, so what I would like to do now is to talk a little bit about the science. And the first thing we want to do is to show you what we're thinking in terms of the core science teams. We're thinking in 3 major pillars, plus an additional one where all the other things might go. You can see the first 2 here. The first one is probably going to be the largest one because it involves everything that has to do with accreting sources. So this is the kind of science that NuSTAR has been the most prolific, I believe, and includes things like active AGN, black hole binaries, neutron stars, all accreting sources, ULXs, TDs, blazars, sources that are in high accretion mode, low accretion mode, everything goes in there. So you will see some names attached to these pillars. These are the people that we've been talking to, and they have agreed to help us to organize each one of these groups. So they will be in charge to start adding collaborators to the working groups and organize how the science topics are going to be developed for the proposal. The second pillar, it has to do with endpoints of a stellar evolution, and that includes nearby galaxies. We also wanted to put there the galactic center because the galactic center is sort of a complex situation where you have many sources. You could do, of course, you could do binaries, you could do accreting sources there, but it's a whole thing by itself, and it's more into it falls better into the category of galactic surveys as well. And all the science related to supernova remnants will go into it as well. So Brett will probably talk about some of it later. And then the third pillar has to do with black hole growth. By the way, I should mention these pillars were chosen accordingly to the Astro 2020 decadal, the main programmatic points that they address in the survey. So the last pillar, it has to do with obscure AGN and surveys. A lot of the science we heard in this last day will go into that section. So then, as I said, there is an actual fourth pillar, which is not part of the major decadal points, but we figure there is all this additional science that might not be necessarily into the super core of the mission, but it's still very relevant. And there's a lot of people that might want to contribute to tell us how a mission like HEX-P could help out on this. And this includes other time domain science, dark matter decay, measuring the Hubble constants, galaxy clusters, and tests of GR. Some of it, again, we heard in this conference. So I'll now talk about the science, some of the science topics that we're thinking about. If you heard my talk yesterday, or if you were in the HEX in the head meeting in the US a few months ago, you're going to see pretty much the same. But one of the core science for the first pillar in particular has to do with understanding black holes. Is that a problem with the screen?
No, go ahead. Go ahead.
Okay.
You go ahead.
Of course, black holes are still extremely interesting sources. They help us to understand fundamental physics. They are the endpoints of stellar evolution. So there is a connection to understand how every star evolves. And they're also key players in the cosmological history of the universe, how galaxies are formed through feedback and all these processes. They're obviously tightly involved. But meanwhile, all this complexity can come down to, by understanding a black hole, you only need two parameters, the mass and the spin. So that makes them, in a way, very simple objects at the same time. In all this, the common denominator is accretion. Accretion is a process that ties the black hole with the environment, and at least for X-rays, this is our way to observe them. So I've shown this before. We want to measure supermassive black holes spins, especially in a large sample, because the distribution of spins will tell us something about how they form. In particular, if you look at the spin versus mass, they will tell you how they acquire the mass, what is the formation history, whether black holes are formed through mergers or through a steady accretion. You will predict different distributions, and therefore, if you can constrain the distribution observationally, you can start discriminating between evolutionary models. One particular problem in doing this currently is that, should I do something? Okay, one problem is that we're biased by, we have an observational bias because accretion is a deficiency, it goes like 1/r, and then we tend to see, obviously, the brightest sources are the ones that we want to measure the best. So what we want is to have a more, I guess, a volume limited sample. This is a current, more or less current distribution of spins for supermassive black holes. Everything has been done obviously in X-rays through reflection spectroscopy. I showed this also earlier in my talk. These are recent results by Labani Malik showing the low end, the low mass end of it. And we start seeing some sort of distribution here, but you can evidently see that the error bars are very large for many of these detections. So we want to do a lot better. A mission like Athena will do by itself, will do significantly better. It will do a lot more sources. We're talking about thousands of them with a much lower error bars. The combination of HEX-P with a mission like Athena or HEX-P alone will accomplish something similar, because now we're looking at least a 10-fold increase in effective area. For black hole binaries, it's a similar situation.
We want to measure spins to understand their formation history. How do they acquire spins? It's a big question. Sorry, for the formation of binary, the binary accreting systems. How whether the black holes were born with were formed with a given spin, or did they acquire a spin over time? And if they did, how do they acquire it? Nowadays, there is this very, very new and interesting comparison with the gravitational wave sources that through which we can also have a distribution of spins. These sources in general are not the same population. We know black hole binaries in the gravitational wave detections are have bigger masses than the ones in X-rays. But there is at least one source that is sort of in between, and that's SIG-X1. SIG-X1 is a high mass X-ray binary. It's a kind of source that you would expect to become a LIGO source eventually. And we know from X-rays, from basically every measurement, that the black hole is spinning either at maximum or very close to maximum. So this is a bit of a problem, or I'm not sure if it is a problem, but it's an interesting connection. So something I think HEX-P can do is increase the sample specifically for high mass X-ray binaries, for higher mass black holes. We know the ones that are around here in our galaxy, there are only maybe 3 of them. We want to look more. So for that, we're probably going to have to look farther in nearby galaxies. There is a lot of science that you can do when you increase the effective area and possibly the spectral resolution. We're interested to understand whether we can see emission beyond the ISCO, the innermost stable circular orbit. This is important for the spin measurements in particular. That can give you some idea of the systematic uncertainties that you have in your model. Everything we do right now with reflection spectroscopy is based on the assumption that the accretion disk ends with a sharp edge at the ISCO. And if this is not entirely correct, if there is some emission, even for a small ring inside, that will tend to change to some degree the spins that we measure. So this is just to show a very quick simulation with HEX-P responses. Actually, these are the old ones. I'll redo with the new ones that Kristen just mentioned. I don't think it's going to change dramatically, but this is for a 10 millicrab source in a fairly short exposure. You can differentiate between the assumption of having an accretion disk at the ISCO with maximum spin, or having a truncated disk with low spin. So you can start disentangle the degeneracy between inner radius and spin. Spectral timing, I think, is going to be very, very important in the future of X-ray astronomy, because by looking not only at the fluorescence spectra, but also the properties of the variability, of the time variability, we can constrain a lot more the same parameters and even new parameters like the black hole mass. So I don't have time to go over all these details. Gulo, Mastroserio gave a whole talk about this. So if you can have access to the recordings of the talks, I suggest you to go to that. But this is something we're going to be looking into as well. Am I running out of time? Coronal physics. NuSTAR has been very prolific at measuring coronal temperatures of many AGNs, but the next frontier, or the next step here, will be to understand the properties of that corona. Understanding whether it's a hybrid plasma or not, what's the distribution of the electron, the temperature of the electrons, the distribution, etc. TDEs, we have at least one really good detection with NuSTAR of reflection coming from a TDE that has not jet emission. So this is very new, very exciting. And I can only imagine how much more can you do with an increased area, a tenfold increased area, looking at a lot more sources like this one. The same for changing look AGNs. I showed this in my talk. We start seeing reflection, and we model this reflection in particular for TDEs, seeing features, spectral features that were not seen before. So I'll leave it here. There are a few slides that maybe Dom want to show real quick on ULXs, but if you have questions, maybe I'll take them now.
Yeah, we have time. Take a couple. If anyone has questions. Nope.
Just one question.
Udo
here.
is looking up.
Hi, Ave. My question is about the spin of black holes. So with NuSTAR and with the telescopes that we have now, we measure the spin with a very precise errors. So I don't think that can be improved by these instruments. So what's the improvement? You're going to find more sources, because usually when they go in outburst, we are able to detect these sources even with these instruments. So my question is, what this instrument is going to do.
So you might be thinking more in the binaries cases where we have really good data, but as you see in the plot for the AGNs, it's not true that the spin is always well measured. In many cases, you have a lower limit or an upper limit, whatever. You don't have that sensitivity. Also, increasing the number of sources is important. So both things are important. And even for the binaries, even those papers where you see the spin is 0.999 plus minus 0.001, that is a statistical error of the fit, but it doesn't include all the systematics, right? So if you include those, the errors are larger, right?
You think that like an instrument like this can improve the systematics? That,
of course. Yeah,
okay.
Because then the systematics will come from what is your assumption, things that we discuss here, like the Lampos models versus the non-Lampos, the geometry of the corona, things like that. So you will be able to differentiate those when you have the right signal to noise. Otherwise you can't, right? So that goes into your systematics.
Hi. I'm wondering more about like a programmatic approach to the teams who are going to contribute to that. Have you timelines for that? How big can you imagine the teams to be? Kind of like any of the information, whether you have it right now or whether this is too early?
Yeah, thank you. I wanted to end saying something about it. So we're forming the teams right now, as I mentioned. In the website, you can sign your name to be registered in our list of people, friends, and you will receive the newsletters and all the information. When you register, do we have the capability for them to include which pillar?
Yes.
Yeah.
Yes.
So if you have a particular pillar of the ones that I showed that you're interested, you say, this is what I want to work on, let us know. So essentially the coordination of how many people are going to be in each group is going to come down to the leadership in each group, in each pillar, in each topics, right? So we're building that, and then they will decide, as I said, one pillar might be a lot bigger than another, so it will have a lot more people than the other. But we don't have right now a limit, a pre-established limit on how many people are going to join. We want to be very inclusive, and anybody that really wants to help us and is interested in this, please come and join.
Yeah, we've had discussions with the other probe teams, because what was happening in the US is that basically the Astronomical Society was divided in 4 and everyone gobbled up everyone. And we don't want that to be the case. We want people to be allowed to be in multiple teams. And if you have science that may be covered by multiple observatories, you should be allowed to go and figure out whether your science works better for one or the other. And in that case, maybe make suggestions to how to improve instrument that will make it possible for your science. And so we're going to have a bigger, broader discussion with all the teams. We're going to have a summit. We're going to talk about not poaching each other's support and being open and inclusive so that everyone can go to everyone and join.
And I have a short follow-up question. I guess it is answered by Dom being there in front, but it's not just for US citizens, right? So this is open to the whole world.
Definitely, yeah.
So maybe Fiona knows this better than I do. When it comes to the proposal, when you put in the proposal, is there a limitation there for US citizens? No, there's a no. Everyone is equal here.
I think there's a question.
Go ahead, read it.
Somebody has their hand up. Solon Bauman, do you want to speak now?
Yeah, I could. Do you hear me?
Yes, we hear
Yes.
you.
Okay, excellent. I only wanted to. I'm a bit surprised in the sense that you have a very efficient, especially soft energy telescope, and going down to 1 keV. I'm sorry. Oh yeah, 0.1 keV, and given all that, in your accretion list of studying accretion sources, you have not all compact objects. Basically, you seem not to have white dwarfs included. I wonder why you have white dwarf binaries not included when you're intending to study accretion and basically in all scales. And your telescopes are quite available, suitable for that kind of study.
Right.
So in that sense, maybe going for like compact objects in general rather than specifying neutron stars and black holes. I thought that's a little, I don't know, perhaps maybe would be more integrative to work that way. That would be my suggestion. And of course, given that and other people would like to join and in such a case.
Absolutely. What is in the slide is just and for instance, it's just a quick list of some topics, but each one of the pillars is gonna form with all the science that people care about. So that will include any kind of sources like the ones you're describing.
And just to clarify, the low energy telescope came on a month ago when Athena complementarity got removed. So we haven't had time to adjust our science as quickly, but that's definitely the task ahead. So I'm going to share these slides for you, Dom.
Of course, hopefully most of you are aware that one of the most significant things that NuSTAR has contributed to the ULX field is the discovery of these ULX pulsars. So these are neutron star accretors who are able to somehow reach up to sort of 500-ish times their Eddington limits, which is pretty amazing. So I talked about these quite a lot on Monday, and sort of left you with this thought as one of the key sort of areas that we're looking to attack over the next sort of coming years, decades, whatever. So I mean, there are two major puzzles, I guess, that this discovery throws up, like just how many ULXs are neutron stars and how are these neutron stars able to reach 500 times Eddington or so. So we would very much like to find more of them, of course, and HEX-P is actually something that would be extremely good for this. And the reason I want to emphasize is because if you look at the ULX pulsars that we know about already, the strength of their pulse signal actually rises with energy. So having something with a very, very good hard X-ray response will be a very efficient mission for finding these things. And just the increased sensitivity allows you to go out to sort of do realistic pulsation searches at much lower fluxes and therefore go out to a much larger volume. So I think it's a general comment, but I think it's very clear that HEX-P would be extremely good at finding more of these ULX pulsars. The second comment I guess I would make is that along the lines of how do these sources get so luminous, or at least appear so luminous? One of the key puzzles here is what are the magnetic fields in these neutron stars? And that's not necessarily an easy thing to determine for an extragalactic X-ray binary. We have this one potential case of a cyclotron feature in a ULX pulsar, and that would be the preferred method for making these measurements. But we're sort of pushing the limits of NuSTAR with this kind of stuff, and so naturally having much larger collecting area, having a broader bandpass will give us a much clearer picture of whether these features are there in ULX pulsars. It'd just be much easier to find, much easier to sort of detect these things. And I got onto cyclotron lines as a segue in from ULX pulsars, but of course, the same is true for galactic X-ray pulsars as well. We've got the classic example of V0332 on the left there. So, you can expect HEX-P to do an awful lot of cyclotron line science generally, I would say. And then just the last thing, sort of getting back to the demographics a little bit, again, flash this idea up that with the current NuSTAR data, you can characterize the highest energies in all of the ULX we've observed to date with a ULX pulsar like accretion column. Naturally, with HEX-P, we'll actually get a much better view in the known ULX pulsars of what these accretion columns really look like, we have a fairly crude characterization at the moment. And so we'll also have much better data on normal ULXs, or like ULXs where you haven't necessarily seen pulsations yet, perhaps. And so we should, I expect, be able to test this idea even more rigorously with HEX-P. So that was all I was going to say. Just a few thoughts on ULXs. I mean, I don't know if you want me to take questions. I'm very happy to.
No,
there wasn't very much there for people to ask about.
Yeah, we're running a little, well, we're right on time right now. So let's
Perfect.
keep on time, which means if we have time later, we can return to
Fine.
questions. So next up is Brett.
Okay, wonderful. So my plan is then to discuss some galaxy science with hard X-rays. And, I am nominally in charge of this pillar that includes galaxies as well as now the galactic center, which I became aware of momentarily ago, and supernovae. So please keep those additional topics in mind for a mission like HEX-P. I'd be very interested to hear about ideas for types of science you can do there. But I'll start off by talking about a lot of what NuSTAR has done for galaxy science. And a nice place to start is with this image of M31, this NuSTAR X-ray image that was shown yesterday by Dan Wick. Just for some kind of reference, before NuSTAR and hard X-rays, M31 as a whole galaxy was detected by BAT as a single source. Okay, and so now imagine one single source being resolved into a population of X-ray sources. And clearly this is point source populations that we're just detecting with NuSTAR. And so this is going to be a lot of X-ray binary science, and in particular X-ray binary populations in other galaxies. All right, so in the context of populations, all right, the importance of X-ray binaries is fairly nicely illustrated with this cartoon up here, or both cartoons up here. In the context of stellar populations, right, we form stars as a large ensemble. Over time, they evolve and then go through various phases. So you have to have a supernova involved to form one of these massive stars that are included in these X-ray binaries. And then they will go through dynamical evolution, common envelope phases in some cases. And then in some fraction of the population might become like millisecond pulsars or gravitational waves sources that could be detected by LIGO or short GRBs. Okay, so in that whole evolutionary sequence, there's a lot of astrophysics, right? So we can learn a lot about, just the demographics of black holes and neutron stars. The initial mass function is something that will influence the formation of these populations. We have to know about stellar evolution, binary evolution, and dynamical evolution of orbits, and then the physics of accretion all kind of together. Okay, if we want to understand these populations. I do believe that we are now getting to the point where X-ray emission is actually becoming a useful tracer of galaxy properties themselves. In this example up in the upper right, this is the X-ray luminosity of star-forming active galaxies per star formation rate has been shown to have a nice relation with metallicity. And so, the sensitivity of X-ray binary formation to metallicity sort of gives the implication that X-rays can be used as a potential tracer of metallicity as an example there. All right, but they're also sensitive to other parameters like the star formation activity, the detailed history of star formation in galaxies, stellar mass content, et cetera. And there's reason to believe that, given this kind of metallicity trend, that in the very early universe, as metallicities were very low, X-ray binary populations themselves and their luminosity would have increased. The ionization radiation from these populations in the early universe would have been quite high. And beyond redshift of 5 or so, predictions suggest that X-ray binaries would dominate the X-ray emissivity of the universe, providing a flood of X-ray emission, and that can some of it be absorbed by the intergalactic medium and provide some heating of the universe there. Furthermore, in some of the low metallicity galaxies in the universe, it's hard to understand the production of some emission lines that are observed in the optical and the UV. And X-ray binaries themselves are actually some or a leading suggestion in some cases for how you produce that ionizing emission. Okay, so what have we done really with, or what is so important about hard X-rays, and why would we want to study that with NuSTAR or something like HEX-P? Early on in the NuSTAR mission, we had a nice revelation, basically, that hard X-rays are very sensitive tracers of accretion mode and the compact object type that is in place in the binary population. So this diagram up here is just showing the spectra of hard or black hole binaries in various spectral states, and with observatories like XMM and Chandra that have typically been used to study X-ray binary populations in other galaxies. We're looking at the spectral region that's shown up here, okay? And you can see that through a variety of spectral states, the shapes are not that different, okay? And especially if you have low signal to noise, and then you have the effects of intrinsic absorption on these populations, you really can't tell the differences between these accretion states. But when you move to something that's like a hard X-ray mission, like NuSTAR, you can see that the variety of spectral colors that you would predict for something like variations of black hole binaries is quite large. And this is also not subject to the effects of extinction as nearly as much as something like Chandra or XMM band. And so I believe this was shown yesterday several times by Dan Wick and Jun Yang, but we have formed these diagnostic diagrams based on galactic binaries. So binaries in the Milky Way, where we have very good spectra, mainly from RXTE, where we've observed several binaries at various stages and translated the spectra into various NuSTAR bands. And so this is just intensity of like luminosity, you could think of that, versus some color here, and then a color diagram over here. And then the specific bands are shown right there. The black hole binaries go through this kind of, or can go through this Q diagram where you have hard states shown in dark blue, trends, going across here, transiting into intermediate states shown in green, and then the soft state over here in red. But then for binaries that include neutron stars, okay, the ever-present surface of the neutron star, the boundary layer, actually kind of confines the colors to a very narrow region in here. For accreting pulsars, you have the accretion column giving it very hard X-ray colors over here, and you can see these all kind of segregate quite nicely in this diagram. Not totally in this diagram, but then when you include hard colors over here, you get black holes kind of lying in this region of the spectrum, and then neutron stars over here, with the caveat that ultra-luminous X-ray sources produce neutron star-like colors for the most part. So NuSTAR has been very nice for identifying and characterizing X-ray binary sources with low signal to noise as black holes or likely black holes or neutron stars. And so we've been able to study these populations in other galaxies. So these are some nice examples shown yesterday. I'll go through this somewhat quickly. But with the nearest galaxies to us, M31 and M33, that are not the Magellanic Clouds, you can study with NuSTAR several of the brightest sources using direct spectroscopic studies. And so, there's several bright sources in M31. One highlight is that Tom Macarone found that there were several of these X-ray binaries coincident with globular clusters that were once reported to be likely black hole candidates. With NuSTAR, you can really show that the spectral shape of these is very much consistent with Z-type neutron stars instead. So it was a bit degenerate in the Chandra-like bands. And then this really blue source here is the counterpart to the Swift BAT detection. It's really nicely isolated, has a nice spectral constraint that shows it to be like an accreting pulsar. In M33, you have a really bright, one of the nearest extragalactic, if not the nearest extragalactic ULX, M33X8, that was discussed by Jun Yang. Potentially has some pulsations, but that's still under debate at the moment. Now, these galaxies, these two examples at least, have very different star formation histories, which is somewhat convenient. For M31, most of the galaxy was formed at early cosmic time, so 10 gig a year timescales, and then has decreased in its activity ever since, and it's not really a strong star forming, or it doesn't have a lot of strong star formation activity. But then for M33, this has been a rising star formation history up to the present day. And so the populations in here, now we're tracing different environments, right? You can see in M33 and M being likely associated, the sources are likely associated with young populations, whereas in M31, these are mainly older populations. And then when we characterize the sources that are in these galaxies, in something like M31, that's mainly older populations, we see a lot of neutron star-like colors with NuSTAR. But then for M33, we see mostly colors that are consistent with kind of black hole-like accretors. Now, with NuSTAR, we've been able to push this out a bit further beyond the local group galaxies. We've reliably been able to do these color magnitude or color intensity and color like diagnostics out to about 5 megaparsecs or so. And so a while back, Nevin Vulik, it is now a few years back now, Nevin Vulik had taken all of the NuSTAR observations in the archive, expanding our observations to a variety of environments. Now we pick up things like NGC 253 and MED2 starburst galaxies, unlike any of the galaxies in the local group. And then we can study their binary populations. Now I have to stress though that these are the NuSTAR images of those galaxies at the moment. Okay, and you can see that there's a lot of overlap of these sources. If you look at the underlying populations, there's a lot of binaries underneath the PSF of NuSTAR. So it takes a lot of effort to go and, disentangle the various populations there. But nevertheless, we can produce some first results on the binary populations that are in these galaxies, what the nature of them is, and playing the same kind of game that I've been talking about for the local group galaxies, we can classify the X-ray binary source types into black holes and neutron stars at some level. And then we build up something like this. This is the fraction of, looking over here, this is the fraction of these binaries that are black holes as a function of luminosity, tends to increase and then makes a big jump right around where we see the Eddington limit for neutron stars at about 1.4 solar masses. But still the same. These are very uncertain measurements at the moment, and we really need something like HEX-P to actually get these to be very solid identifications on their types. Okay, so as we go further, we can still look at other environments of galaxies that are somewhat more distant, but we can only do so with NuSTAR using integrated emission. So here I just want to show a result where Kristen Garofoli has looked at several galaxies with varying metallicity. And one of the things that she's found is that the X-ray spectra normalized by the star formation rate shows this increase with decreasing metallicity over at high energies, but then also at soft energies, there's some evidence for some decrease in absorption. So for lower metallicity galaxies, you have fewer metals within the obscuring environment. And so that has an impact on the emergent flux at soft energies. And so we kind of developed this picture here where, this is a movie just showing the spectral variation going from high metallicity to low metallicity. You see the enhancement of X-ray binary populations coming in, and then the decline in absorption as you go to lower metallicity. It's one nice result that was helpful to have the NuSTAR data on. All right, so as we go forward in NuSTAR's 10th anniversary now, there are several additional programs that are underway related to galaxies. Here I've just highlighted a few that are coming up soon. We've recently imaged or taken data for our first elliptical galaxy, Maffei 1. We're looking at the Fireworks galaxy, which I believe is the record holder for number of supernovae in a galaxy. And then we're adding to this, Ann Horschmeyer has a new program to observe several dwarf galaxies at low metallicity. All right, so then for HEX-P, okay, we can imagine, of course, that if we're going to get better sensitivity of these measurements. So at the moment, one of the limiting factors with NuSTAR is if you look at a diagram like this and you look at the sensitivity limit, we actually exclude, and this is for a galaxy like NGC 253 at about 4 megaparsecs, we're excluding the possibility of even detecting soft state black hole X-ray binaries. But then, of course, if we go down, say, an order of magnitude or 1.5 orders of magnitude, that parameter space becomes accessible. And so you can actually see binaries in a larger variety of accretion states. Of course, ULX identification is, or ULX, ULXs themselves are difficult to classify as neutron stars or black holes. It's a subject, a very, very exciting subject, as Dom has pointed out. And so, characterizing ULX accretors is one goal. I mean, just learning about ULXs, of course, in general is very important. And there's going to be lots of ways that we can, sort of do more sensitive searches for, say, neutron star characteristics. We would also have access to monitoring capabilities. At the moment, looking at galaxies with NuSTAR in various observations requires several hundred kiloseconds to get detections at 4 megaparsecs or so. We've been able to kind of look at some of the brightest sources in a galaxy like NGC 253 and at various stages to see if there's changes in accretion states or accretion state transitions. We see some movement here, okay, but the error bars are very large and difficult to get clear classification of what's going on. And then finally, of course, if we have higher sensitivity, we can push out to larger distances. And the game is, as you push out to larger distances, you are able to now study X-ray binaries in new environments. Right now, it's very difficult to even study X-ray binaries at hard X-rays in elliptical galaxies, for one example. But then, of course, going out to higher or larger distances will allow this. All right, so I will conclude here with my last slide, just as a somewhat sort of a motivator. Sometimes when I show this slide, I usually start with just a black screen, and then I transition to this. Okay, so this is NuSTAR's first view of NGC 253. So the black screen would have been something like if you looked at this galaxy with RXT, you'd see nothing, but now you can see something. With HEX-P, we transition to something like this, right? We're now looking at significant numbers of sources in other galaxies and getting a lot more information about the populations. All right, so I'll leave it there and just flash up a little bit of a reminder of some of the stuff that we're looking forward to.
All right, well, thank you. Well, let's do the clapping. We have time for a couple of questions on this topic. If we have any, I think I saw a hand.
I refuse to leave until I get one question.
I thought we saw a hand go up somewhere. What are you doing? Oh, here. Go ahead, Dan.
Yes.
So I guess you almost answered it with this cool simulation of what HEX-P would see. How much of these additional sources are due to just the greater sensitivity that HEX-P would have? And how much of it is, if any, improvement in angular resolution that you're separating more sources? I guess, is it more about the sensitivity, or does HEX-P have enough of an improvement over NuSTAR in terms of its angular resolution to help out?
Oh, absolutely. I mean, it's a factor of 10 improvement in angular resolution. Background, a large problem was disentangling, the contributions from various sources here. That will be made a lot easier with higher resolution. And just higher resolution, of course, increases your sensitivity alone by having less background in your data set. But all of it helps. But I think the higher resolution is a big deal.
I was hoping for higher resolution, but seeing it, I think, is pretty awesome. Thanks.
Cool.
Any other questions? We have Neil Brandt, if you want to speak up.
Sure, I'll do my best. Can you hear me okay?
Yeah, we hear you fine.
Yes. So, Brett, you pointed out, of course, the very interesting dependence upon metallicity and how metallicity may be affecting the evolution of binary systems in various ways. How well is that underlying physics nailed down? Is there still a lot of work to be done there on the details of why lower metallicity systems are better X-ray producers? And can, of course, HEX-P clarify that further?
Yeah, I mean, the physics is, this is a prediction that has come from population synthesis models directly before we've even observed it empirically. And the reasoning for it is, as binary systems evolve, they lose a lot of mass from stellar winds. And, higher metallicity stars will lose more mass from stellar winds. That has the effect of widening the binaries. It has the effect also of producing compact objects that are of a particular mass, but with lower metallicity, with a lower abundances, you would produce more massive compact objects. And so those are the driving factors. However, theoretically, that particular relation is not well understood. Okay, so there are a lot of ingredients, as you know, that go into population synthesis, and so some of them can produce opposite behavior. Yeah, I would say no. And for further your question regarding HEX-P, clarifying that dependence, I don't know the answer specifically. If there is some way that HEX-P is sensitive to accretion of more massive compact objects, if it's able to show that could very well be a nice observation that would be helpful for that particular case.
Yeah, that's what I was hoping is
Okay.
if there's some way that HEX-P could break underlying degeneracies between those factors and tell you the answer, that would be a powerful thing. And it might be worth thinking about that further.
Yeah. I mean, the enhancement observationally, just so you know, is through the ULX population. Okay, so that's very difficult. But if we have a nice way of knowing whether there's black holes versus neutron stars and ULXs, yeah, certainly.
We will figure it out.
Yeah, we'll figure it out.
Okay, let's move on to Daniel Stern. Dan, are you ready?
I am ready. I am sharing my screen.
Yeah, we see this. Well, I see it. Yeah, we see it on Zoom. We don't quite see it here yet.
I will start and trust that you are going to get it up on your big screen in a second too.
We got it. Go ahead.
Okay, so I'm going to talk about the third major pillar of black hole growth over cosmic time. Though, since I'm the last talk of this whole meeting, actually this 3-day meeting about NuSTAR, I just want to really quickly thanks for all the people who came to Sardinia, all the people who called into Zoom, and then people like me who came to Sardinia and called into Zoom for coming to help us celebrate 10 years of NuSTAR in orbit. My son tested positive for COVID on Monday morning. I'm testing negative, but for safety, I stayed in our Airbnb. Anyhow, thanks for celebrating with us, and thanks for making NuSTAR such a huge success. We heard 3 days of talks from everything from Jupiter to high redshift blazars. One of the key things was just hearing how essential NuSTAR has been for playing well with others, for coordinated observations with XMM for a decade already, but more recently with HEX-P, and then plans for XRISM coordination in the future. I think at this point, about half of NuSTAR observations are coordinated with various other observatories for various reasons. And special thanks to Matteo Bicchetti, my co-conspirator in the science organizing for this committee, and then Luisa Serra and Cassiopeia for doing the local logistics, doing a great job. And sorry, I'm not there with you in person. And then just one other NuSTAR thing. We heard a lot of exciting results over the last 3 days. If you have any exciting NuSTAR results came out very recently, or not even that recently, contact myself or Brian or Kella Cofield, who's the media lead for NuSTAR at JPL. And we have great graphic artists, and we'll help you develop stories that could go on the NuSTAR webpage or could be a bigger NASA press release. Anyhow, back to HEX-P, black hole growth over cosmic time. This is one of the big places where HEX-P will make big advances. And I kind of see 3 main aspects to this. One is resolving the cosmic X-ray background. Second one is X-ray faint populations. And then third is mergers. And time permitting, I might talk about a little bit additional HEX-P science outside of this. So a figure that hopefully is familiar to a lot of you. 50 years ago, we measured the cosmic X-ray background, had a distinct shape to it that peaks at 20 to 30 keV. It's the sum of all the X-ray sources in the universe. Unobscured sources are relatively flat in these units, whereas if you add obscuration, you preferentially lose the soft X-rays. So the shape of the X-ray background told you right away that there's a lot of strong contribution from obscured AGN. But for the last 50 years, X-ray astronomers, one of the big goals has been to try and understand the sources responsible for the cosmic X-ray background. Are they higher luminosity, lower luminosity? what redshift, how does it correlate with the various properties of the galaxy? And if we can understand the source populations responsible for the cosmic X-ray background, then we understand the cosmic history of black hole growth, since most of this is coming from supermassive black holes in the centers of galaxies. So then we understand the growth of supermassive black holes over cosmic time. And we think that growth has a large feedback process with the growth of galaxies. So understanding this cosmic history of black hole growth helps us understand galaxy formation. In the lower energy X-rays, we're more than 80% resolved. You're down at 2 keV, it's well above 80%. If you get to the end of the XMM and Chandra band passes, it drops. NuSTAR, with its deepest observations published so far, resolves about 35% of the X-ray background at its peak. And with HEX-P, we really can make huge strides. Here's some simulated images by Francesca Chavano and Ryan Hickox from a couple of years ago, a slightly different version of the HEX-P design. But you can see on the left is an image of the cosmos field, and then on the right is a HEX-P observation. I think this is 60 kiloseconds observation, so comparable exposure time for the two images. HEX-P design is modifying, so maybe it's 100, 200 kiloseconds now. Still, it's not megasecond depths, and you move from seeing a handful of sources to several dozen sources. So HEX-P between the lower background, the tighter PSF, and the more effective area really is a sea change for doing extragalactic surveys. On the left is that image showing it's just a zoom in from a larger simulation they did. And then on the right shows you the resolved fraction of the X-ray background as a function of energy, based on a figure from a paper by Ryan that he's just finishing up now. But at the bottom, you see this blue line shows you the deepest exposures with NuSTAR directly resolve about 35% of the cosmic X-ray background. With HEX-P, with 100-ish kiloseconds, you start resolving about 70% of the cosmic X-ray background. And then if you start stacking, the lower energy sources detected by HEX-P in the higher energy band passes, we're looking at getting 90% of the cosmic X-ray background resolved, really solving this question that's been decades long in the X-ray community. And then this is just from their simulation, the luminosity redshift plane. The black squares at the lowest, at the highest fluxes, that's from Swift-BAT, which largely just goes out to normal AGN out to redshift 0.2-ish. Beyond that, these are all blazars at the higher redshifts, so not quite the same beast. The orange and the green and the blue are the NuSTAR surveys pushing out to redshift 2, and then the HEX-P simulation really gets well beyond L-star, pushing out to, cosmic interesting times, peak times of black hole growth, getting down below L-star. And so a range of questions from that. One of the big questions, just the distribution of obscuration, how many galaxies or AGN are unobscured, how many are heavily obscured, how many are Compton thick. We heard a range of talks about this over the last couple of days. The Newland surveys that Peter Borman talked about and is nearly, it was close to submission, probably one of the best results so far from NuSTAR. And we're getting about 40% of this infrared selected sample of sources are Compton thick, starting to overlap with the latest population synthesis models from Tanima and Nana, and doing a lot better than with Swift-BAT. The Compton thick AGN, you're really, even though BAT sees sources out to redshift 0.2, the Compton thick sources really are the nearest edge of that and really aren't able to study the cosmic evolution of that or even really do a great measurement of that fraction of Compton thick AGN. And this is a place where these all have fairly large error bars. With HEX-P will do a lot better. We also saw a couple of talks over the past couple of days showing this, and various samples have shown that as you go to higher luminosity AGN, it seems like there's more, the torus covering factor falls, or there's more viewing angles down to the central engine. This is a paper a couple of years old by Murray Brightman, there's some more recent work showing the same trend, but the error bars you can see are have something to be desired. And this is a place where HEX-P, just higher signal to noise, larger samples, we can really measure this well and try to understand this. And this is telling you something about the feedback from the AGN as it goes up to higher luminosity. This holds for kind of isolated AGN. As you get into mergers, this plot falls apart. And then I grabbed one slide from Kristina Keleva from her poster. Just it was easy to grab posters, but here's modeling of a nearby heavily obscured AGN NGC source, NuSTAR, and then HEX-P simulations. And you can see with the NuSTAR, even though this is a relatively bright source, the error bars are large. Really separating out different models is difficult. With the HEX-P, you really can start digging into the different models. These models vary from essentially the torus height and the covering factor of this inner cloud ring in the UX-Clumpy models. My suspicion is just like NuSTAR really forced a new generation of AGN models and torus models like torus and UX-Clumpy. HEX-P will push that the next level. And then finally switching over to another type of X-ray faint population besides the heavily obscured guys are one that Neil and his students and I have been working on for a while. And this is one that really confuses me still. And I don't think NuSTAR is ever fully going to answer this. But we see these sources, especially BAL, AGNs, like Markarian 231 is a classic one, where in the UV, they look pretty normal AGN. You're seeing all the way down to the broadline region. They look like relatively unobscured AGN in the UV, and yet in the X-ray, they're very, very faint. And so the question has been, are they faint because there's some sort of shielding gas close in to the AGN that's hiding the X-rays, but it's close enough in that it's not hiding the UV? Or maybe there's something happening to the corona and the corona has collapsed, it's cooled down, the corona is very faint or weak for some reason. We've been a range of papers on this and pushing one way or the other, but I don't think we really have a confident answer on what's going on. And I think this is really interesting because in particular, Daniel Proga has some model predictions from more than a decade ago that if the corona gets weak, you change basically your ionization state in the accretion disk, and it can make it so that it's easier to blow broad absorption lines. So it's easier to have more feedback from the AGN. And so I think 10 years ago, I would have thought BAL, AGN, like every quasar was a BAL if you looked at it at a certain angle. And these sort of models predict that maybe it's an evolutionary stage, and those winds are important for feedback into the galaxy and how the AGN carves out the star formation in a galaxy.
5 minutes, Dan.
Okay. And then another place where faint AGN, well, I kind of have two hats. I've done a fair amount of work in the infrared, and there's a kind of a classic Stern plot in the infrared. I'm not going to talk about that. The X-ray version of this Stern plot has been my bugaboo for years, since the beginning of NuSTAR. And I've had the same result for various sources selected in various ways over several years now, where I have some luminous AGN selected in some way, typically in the infrared. I look at it in the X-rays and I get a non-detection. And then I get teased by the rest of the NuSTAR team for, yet again, not getting any NuSTAR photons. This is a Y-selected source, redshift 0.4. You can see at 10 to 40 keV, if it was unobscured, you get this solid black line. If it's 10 to the 24 column, you get this gray line. It's all the way down here. So is this got a crazy absorption column, 10 to the 26 or something? Or is there something happening in these sort of sources, these infrared selected, very luminous AGN, which makes the corona very weak? And with the non-detections, we're not able to answer that. With HEX-P, I want to turn my non-detections into detections and really answer these questions. And then finally, on black hole growth, mergers is clearly a very important part of black hole growth. We saw various slides showing the same result over the past couple of days, but here's one from Mike Koss, 2018. If you look at early merger stage. So galaxies are still several kiloparsecs apart. Some of the AGN are obscured, this blue line, but a lot of them are unobscured. If you got to larger distances, that even more of them are unobscured. But when you get to the interesting close, few kiloparsec, sub-kiloparsec separation, AGN, a very large fraction of these mergers will show obscured AGN. Dust gets kicked out. Maybe stuff is kicking in nearby the AGN as well. And so if you want to really understand mergers and AGN activity during mergers, you really need something that's working above 10 keV. Chandra or Axis isn't going to be able to do it the same level. You can do it with a hard X-ray observatory. And that moving from a 1 arc minute PSF to a 5 arc second PSF, NuSTAR to HEX-P really is a huge gain as well. There's a whole other range of HEX-P science, time domain things such as kilonovae, tidal disruption events, cluster science, galaxy clusters, some of the things that we've heard about before, relativistic explosions. I think it's a very exciting observatory. I think that if we only have one sort of flagship class mission in the 2030s in the X-rays, I think this is the one that you want to have. It lets you do follow-up of events found by LSST, lets you do broadband spectral studies, and then it also plays well with some of the newer observatories, which hopefully will still be up in the 2030s, like XP and XRISM. And so I'm out of time. I'm just going to skip over those. I'll do one. Just NuSTAR has set some of the strongest constraints on dark matter particles models. So this is work led by well, MIT group moving to Columbia now. But with HEX-P, we'll make even stricter limits. We're really knocking out some of the whole parameter space for various dark matter particles. With NuSTAR, and then HEX-P will be even better. So to get involved with HEX-P, Kristen showed this as well, but I want to just end with this slide, hexp.org. You can sign up there. You can email any of the people you see up on the stage or myself. And our website also has a link to our white paper, which is publicly available from ASTRO 2020. Thank you.
Do we have any final questions? Everyone is tired. Oh, we have one on this. We have two slides. So it was Tonima. Please go ahead.
So my question was about these very luminous sources. Is there any way of getting a mass measurement on them to get any Eddington ratio measurements to see?
Yeah. So with the heavily obscured AGN, so some of those ones that I was talking about, that IR luminous AGN that I don't see in the X-rays, they're often so obscured that we can start seeing the host galaxy in the optical near IR. And then if you take a bulge mass, black hole mass relationship, or sometimes, some of them we see broad lines even weakly, though I always worried whether we're seeing winds versus the BLR. But anyhow, we have a couple of papers I'm co-author on, which suggest that they're super Eddington, or very, kind of Eddington ratios of 1.
Okay, so in that case, maybe it should also show the spectra. This should also show maybe signs of outflows, because even if it's heavily obscured, the obscuration maybe can last around the AGN for a few million years while it's like flowing out. That's something we were considering for, according to what we found with bad data. But yeah, that's something we were thinking would be happening.
Yeah, let's talk to Nina.
Okay, thank you.
Right, Neil Brandt.
Hi, Dan. Thanks for the nice talk. Related to your last slide, and my apologies if I missed this in one of the other talks, what is the ability of HEX-P to respond to transients? What would be the time scale to get on source? How many such requests might be accommodated per week or something like that? Or is that not yet fully defined?
Definitely not fully defined. We're early in the whole process. So we are soliciting, what the community wants, and we will try to build something that's able to do that. NuSTAR, NuSTAR, we were thinking we would do about 1 TOO per year, and that's what we designed for. And now we're doing, multiple a week. So hopefully we'll design this knowing that the community is going to want that.
Right. Yeah, certainly. I would, exactly as you say, community, I think, would probably want it. Are there fundamental constraints, just given the nature of the mission, given its length and so on, in terms of its ability to get on targets on a certain time scale?
Yeah, so you're worrying about the long mast and how fast you can slew. Again, it's Brian and I were just talking about this recently. It actually, if Brian wants to answer, he's welcome to, but NuSTAR actually slews pretty quickly.
Yeah, I don't think it's not going to be the slewing speed that's going to limit it. It's going to limit the ability to upload in time. You need to go through, make the ATSs and upload it, and you have to people. That's what's going to limit it, not the slewing ability, is my opinion.
Yeah. And has NASA clarified the capabilities to communicate with the probes on rapid timescales and how that would work?
No, not yet. No.
Okay.
And I don't know if they plan to.
I guess the NASA's running this TDAM, time domain and multi-messenger astronomy meeting in August. So I think that's the perfect venue to bring that up, Neil.
Yeah, I mean, if that is indeed the tall pole limiting things, then getting clarification as to what the probes have to work with could be quite valuable, I might guess.
Definitely.
I think it's engineering, Neil, and I think we can do quite a bit better than NuSTAR with more money and designing from the beginning for it.
Okay, thanks a lot.
Okay, well, I guess we are out of time, and I want to thank you all for sticking around, and I want to thank the panel. So let's just give us all a round of applause. You're free. You're free, go.
Maybe Matteo wants to say something.
Matteo, do you want to say something? He looks like he wants to say something. Well, we want to thank Matteo too. Okay.
But we should give you a round of applause.
Yeah, we will.
This is all thanks to Matteo. Thank you so much, Matteo.
Thank you so much. It's been a fantastic ride. And now safe travels, have a fantastic dinner, enjoy the rest of your stay, all of it. Okay? Thanks a lot.